Okay. Okay, so we'll continue from where we stopped yesterday. Um, Still talking about FRI. So we have looked at Merkle trees, right? Committing, proving, and verifying. Then we looked at Reed Solomon. Okay? So you take a vector, you interpolate it to get a polynomial, and then you evaluate that polynomial at more points to add distance. Right? Now we are trying to figure out how can we be sure that this code word represents a polynomial that's no more than degree d. Okay? We're trying to prove the bound of the code word. So maybe like the polynomial, the original polynomial must not be more than degree 5 or degree 8. So that's where we are now. So what that's called is like the Reed-Solomon interactive oracle proof of proximity. I'm going to write it now. So it's called the Reed-Solomon interactive oracle proof of proximity. Okay? So proximity is talking about distance. So they are trying to prove that the code word that you have, so you started with a polynomial, then you converted it, started with like values in a polynomial, and you converted it to a code word that is longer, right? So now you're trying to prove that this thing is a valid code word, or it is close to a valid code word. In the sense that it is a code word, then it can only be like somewhere here, right? It should be close to a valid code word. So that's the goal of RS, interactive oracle proof of proximity. So this is what I was talking about yesterday, where you reduce the code word, you fold the code word into half, but then the degree also goes down half. And then you keep on doing this until you get to something that is like good enough for the verifier to just check by itself. But before we start this, let's talk about roots of unity a bit. Roots of unity. Yes. Roots of unity a bit. So, in order to facilitate the folding that we're about to do, we need the interpolating set to have a special structure that is like amendable to folding, right? And not just like fast folding. So roots of unity usually cares about, so you want to fold like the code word into something half the size. We want a special structure for the interpolating sets. So people use the roots of unity because like it's fast for FFTs, but then it's also like good for folding. So we'll talk about roots of unity first, and then why it is good for folding.
Just to be clear, folding is like trying to get back the now.
It's trying to reduce this code word, right?
Yeah.
That you're saying that it's supposed to be of degree, let's say 8. The way you can reduce this, right? Yeah, to 4. The way you can check that this thing is degree 8 is by interpolating and then checking the highest power of x. But then we're assuming now that the top one is too large for the verifier to do that work by itself, right? So instead, the prover and the verifier follow this dance where they make the work smaller. So they do a folding where they now get something that is not like of degree. You get? And then they do it again where they get something that is of degree. And they do it again where they get something that is of degree. Okay? So now once they have gotten something of degree 1, that's small enough for the verifier to be able to ascertain that yes, this is indeed degree 1. But then that's not enough to... So ascertaining that that's degree 1 is not sufficient for knowing that the original thing was degree 8. So you need one more thing. You need to prove that all the foldings were done correctly. So if the prover is able to show the verifier that I folded these things correctly and I only folded 3 times and the base is like degree 1, then that must mean that the top one must have been bounded by degree 8. I don't know if that makes sense. Because folding is like breaking in half. Then if you know that I did it 3 times, then you know that, okay, if I'm seeing something that is of degree 1 now, that means the last thing I must have seen must have been of degree 2, the last thing I must have seen must have been of degree 4, and last thing must have been of degree 8. And that way you are sure that that top one is bounded by degree 8. Does it make sense?
So irrespective of the degree of the point,
Yes. To stop. What do you mean by the degree of the folding?
So, looking at a very high degree, so can you just if we're supposed to break the point, we need to do every step to be now. Since we have 4 here, can we make it? Is this supposed to be just even? Or
I mean the degree?
Yeah, or you can make it higher multiple.
No, it doesn't have to be just even. Like that 8, it doesn't have to be 8. It could be more than 8.
Sorry, you want to use?
Oh yeah, I'm coming.
If it's a very high degree, so you have to keep on running that point.
You have to break it down, yeah. But then it seems like you're breaking it in half. And then that's like log base. So regardless of how large the degree is, reducing it like that is not expensive. Like let's say you had like degree 1 million. I don't know if this is correct. I don't think this is correct. This is not log base too. Yeah. Should be like 19 or so. 19 is bad. So that would be like 19 steps or 20 steps. Then there's also a way to like fold it so that the degree is not just halving. Maybe it's like 1/4. You get, so it's like every time you are reducing the degree by 4, not by 2. Not by 2. And it's also possible that the verifier might say that I don't need you to get to degree 1. I have enough computing resources to verify, let's say, when it is degree 4. Right? I can do that interpolation by myself. Yeah.
So this is where we use 4. When we divide it by 4, we have to get the consistent, so we can do 4 to...
For FRI, consistent. For FRI, consistent. But I think there are ones that have come out now, like where. There's a new this one called where, and stare. So they are like adaptations of FRI to make the verifier faster or something. So I think one of them has this inconsistency built in. Cool?
Yeah, so what if the degree is not in?
Yeah, you just divide it by 2, but then take the seal.
Or you think it's in?
Yeah. It's like we are bounding it. Yeah. Yes. You are testing that the degree of the original message is within a certain bound. Because that's something you need for polynomial commitment. It's not just that you have committed to the values, but that the degree is what you want the degree to be. Make sense? So, yes, so with Solomon interactive proof of proximity, that's this test. Now, but I want to talk about roots of unity a bit. Yes. So for roots of unity is just 1. It's like 1. Root of unity is like root of 1. Okay? So there's something called like the nth root of unity. So maybe like the second root of unity, or the third root of unity, or the fourth root of unity. But the idea is that x raised to the power of n should be equal to 1. Right? Where x is the nth root of unity. Right? So like if you want to find if n is 1, that's like 1. So that means that x is going to be what? Well, they call this root of unity thing omega usually. So let me just follow so omega. So let's say n. If n is 1, then the root of unity is just 1. Like omega is equal to 1. Does this make sense? Because of 1 raised to the power of 1 is equal to 1. So it checks out. Now let's say we wanted the second root of unity. So nth root of unity is kind of like nth square root of 1. There are going to be multiple values. So in this case where n is 1, it's like, which is just like 1 technically, right? I don't know if this is correct. But you get the idea. Then if you want to do the second, so you're looking at what value, so 1, right, for 1 raised to the power of 1 is equal to 1. This is the condition, like omega raised to the power of n is equal to 1. That I'm calling omega. What is the other one? What's the name for W?
No, this is omega, but this small letter omega.
So now for the second root of unity, right, we're looking for an omega such that omega raised to the power of 2 will be equal to 1, right? And that's the goal. And we're going to have 2 such values. In this case, there will be so like when you do omega raised to the power 0 and omega raised to the power 1, we're going to get 1 and minus 1, right? Because 1 raised to the power of 2 is what? Minus 1 raised to the power of 2 is what? Are you seeing it? So there's a way you can do this, right? Like just do the square root of 1. That's what? Okay? So this is where like n is equal to 1.
From a definition, w is for n equal to 1, where x is.
Sorry, not x. Initially I wrote x equal to. Make sense? So square root got us 1 and minus 1, right? So this is now for like n equals what? 2. And we have 2. N equals 2. Then I think the next n is 4. Square root of 1 is what? 1 and minus 1 again, right? But now what's the square root of minus 1? I am minus I, right? Are you seeing it? So now these are now like 4 values such that if you raise them to the power of what? Is it 4? They will all give you 1. Make sense? So like 1 raised to the power of 4 is 1, right? Minus 1 raised to the power of 4 is 1. I raised to the power of 4 is what? How?
Minus 1 raised to the power 1 over 2 times 4. Minus 1, I is
I square root of minus 1.
minus 1 is power 1 over 2.
Right?
Minus 1 square. Times 4 rather.
Right? Right? Make sense? And out of the other one, minus I. That would be what?
That would be that would be that minus is still the same thing as I raised to power 4. You can just do minus I times minus I times minus I times minus I. That is I raised to power 4.
So you're already removing the minus just because of the power
Or
is
you can
even.
even factorize minus 1. Factorize minus 1 out. Then you have minus 1 times I, everything is to power 4. Then you do minus 1 raised to power 4.
Then I raised to the power 4.
I squared times I squared.
So at the end of the day, it's still like I raised to the power, which falls back to, which is equal to. Do you get? So now all values there, raised to the power of 4 equals 1. Okay? And then you can get this for, so it depends on the field. You can get this for different values of n. So Arcworks has, yeah,
Basically, the value of n is 2 raised to power something.
I think I, EI,
No, ZEI, 2 raised is exponential.
yeah,
So we are
natural, I'm coming. Yeah, continue.
When n is 1, like we are just, it's just 2 raised to power n minus 1. When n is 1, that is 2 raised to power 0. We are getting 1.
Mm-hmm.
Like one solution. When n is 2, like 2 raised to power something. When n is 2, we are getting 2 raised to power 1. And that is 2 solutions. When n is 3, you get what I'm saying?
I'm coming. Is there n equals 3?
Sorry, n cannot be equal to 3. But what we are doing is just 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. Powers of
Yeah, powers of 2 for n. Yeah. Okay. So this is Arcworks. You know how you have, can you guys see this? So you know how you have prime field, right? There's another one called FFT field. FFT field is also a prime field, but it has, it's also a field, sorry, but it has a new function in it now called get roots of unity. Okay, so you can use this to get the nth root of unity. So it will return to you an omega value. Now this omega value, when you raise it to the power of n, you are going to get 1. Okay? But you can also use this omega value to get all the n roots of unity. Does that make sense? You know how we had like for when n equals 2, we had 2 values, right? When n equals 4, we have 4 values. If n is equal to 8, we're going to have 8 values. But then there's one generator that can generate all of them. Okay? So in this case now, I think the generator is minus 1. So the way you generate everything is that you take generator and you raise it to the power of 0, then raise it to the power of 1 for 2, right? It's 0 indexed. So it's going to be like, to generate the entire set, it will be minus 1 raised to the power of 0 and minus 1 raised to the power of 1. What would this give you? 1 minus 1, which is what we have here. But we got it from just one value. That's the generator of the roots of unity. Okay? Now, in this other case, what would generator be? It seems to be something I, minus I. I guess. So let's try minus I. There's a way to get it exactly. There's like a formula that you can use to get it exactly. So but Aquox has already given you like a function that will just give you that generator like straight away. So let's assume it's minus I. So that's going to be minus I raised to the power of 0, which will give us 1, right? Then minus I raised to the power of 1, which will give us what? Minus I. Then minus I raised to the power of 2, and minus I raised to the power of 3. What's minus I raised to the power of 2? Hmm? No, raised to the power of 2. Minus 1. No. Is it 1 or minus 1? Right? The 2 will disappear, so it's not going to be negative. So it's not I times I, which is square root of I times square root of I, which is just minus 1. Then what of minus I raised to the power of 3?
Minus I.
Wait, that would be minus 1 times that's I.
Minus I.
It's I. It's minus 1 times minus I.
Yes, now.
That's plus I.
Wait, you said minus what?
Minus 1 is power 3 is minus I raised to power 2
Wait.
times minus I.
Well, I did minus I raised to the power of 3.
Uh-huh.
So it's minus I raised to the power of 2 times minus I.
So you said minus I raised to the power of 2 times.
minus I. So that's minus 1 times minus
Makes sense? So,
Sorry.
yeah,
I don't know.
it doesn't make sense.
It makes sense. The general formula, irrespective of the data we are, there is something like that.
There is a.
There is e raised to the power of 2,
Yes.
2 ki
Yes.
over n.
What of pi? There's no pi there.
Sorry, pi is what?
Yeah.
2 pi ki over n.
Yes. Wait, call it out. Let me just write it.
E raised to the power of 2k or 2 pi ki over n.
So this will give you. Yes. No, this will give you the generator. So when n is equal to 2, right? It will give you minus 1. It's a minus 1 that we're able to use to generate everything. When n is equal to 4, it's going to give you minus I. It's going to give you minus I. Does that make sense? But you don't need this because we're not working with complex numbers. We're working with fields. So fields have their own. That's what that formula, that function I gave you, this one, get root of unity, is going to give you the generator for that nth root of unity. So you can now do that one raised to the power of 0, raised to the power of 1, raised to the power of 2, up to n minus 1. And then you'll have the full root of unity. Does that make sense? Okay. I was saying that Aquox has FFT field. Should we just run this?
Excuse me. Complex number. Are they not
The fields that we're using.
fields? Now.
The ones we're using. The ones that you're using in Aquox. You can.
Let's see what that I will produce. The root of I.
It's not looking nice.
Apparently, it's not that.
It's doable now. So I'm coming, Rima.
Why is it mutate with?
Huh?
Why is it mutate with? Why is it mutate with?
Why is there?
Why is it
Oh,
mutate
no.
by
It has to be a power of 2. Why it has to be a power of 2? That's what I'm thinking about now. The condition is that all the values raised to the power of, like, in this case 3, right, must be equal to 1. So what's the third root of 1? Is there only 1? Can't be plus or minus. Go. Raised to the power. I need to,
Is plus or minus one. Oh, sorry.
so in that case now, and I think there's also the condition that you need n values also, right? So like, if it's the second root, you also need 2 values. Sorry. If it's the fourth root, you need 4 values. If it's the 8th root, you need 8 values, and like that. But I don't know why that's not like a legitimate reason yet. But it's the best I can come up with right now. So when you're doing odd, you can never have a negative again, right? It has to just be like positive. Because negative will always give it back negative, and you want to get to 1, which is positive. So that already like restricts the amount of values that you can have. But then what's stopping just like arbitrary evens from working, right? Like, why can't we use 6? Why do we have to go from 4 to 8? Those kind of questions. Yeah. But the reasoning, there's another reason for all of this. We're going to do folding, right? So we want to go from something to half. Yes. And then want to be able to get another half again. That's only really possible in powers of 2s, right? Because if you start with like 6, yes, you can break it down into 3, 3, right? But then when you're at 3, you can't break it down into half anymore. It's like 2, 1, right? But then if you started from something like the power of 2, you can break it down all the way to 1. And there'll always be half, right? Regardless of any power of 2 that you start at. So a combination of all those things is pointing towards a reason, but that's not the reason. Those ones are just like pointers.
So, specifically for our use case,
We need,
full power.
yes, so I can always break. Because we're doing fry. I want to always breaking in half. Yeah, let's do this thing. So square root of 1 is what? Square root of minus 1 is, now square root of I.
Instead of I got
I use a lot too. Not for writing code. And I use Grok too. Grok is actually better right now for reasoning. Yeah, for reasoning. Like, it's really good for reasoning. Yeah, DeepSeek is good too, but it's slow. Yeah, the reasoning takes a really long time before it gives you the answer. ChatGPT. Yeah, I'm coming. What's square root of I? Brah. This square root of I, ladies and gentlemen.
so are we actually using the value of you?
Huh?
Are we really using the value?
Which values?
The root of unit value?
Yeah, we're going to use it as the interpolating set. We're going to use it as the interpolating set of our, like, when we're going from our polynomial to a code word, yeah. They're going to evaluate that polynomial at all the roots of unity. And there's a reason, because of the folding.
What's now the n? What is the size of n?
The n is the size of the code word, right? So like, that blob factor, the message times the blob factor, is what gives you n. But it has to be a power of 2. Yeah.
Okay, that should be a power.
Yeah, it has to be power. Yeah. It has to be power 2. for multiple reasons, for FFC and for, so like 1 plus I divided by root 2 minus 1 plus I, message length, and message length is K. Block factor is, I don't know, they use a symbol for it. So. Okay, what's square root of minus I? Okay. So now all of this, if you raise them to the power of 8, they will all give you 1. But are you seeing a folding already? You should start seeing a folding. Like, starting from 8, right? You fold to 4. Then you fold to 2. And you fold to 1. How do you fold from 8 to 4? You square everything. Okay? If you square everything, if you square 1 and minus 1, both of them will give you 1. So there's an overlap. Square. Square 1, what will you get? Square minus 1, what will you get? Square I. Square minus I. So 2 elements in that nth root of unity, when you square it, it will give you the same element in the next root of unity. This is the key thing that FFT takes advantage of. It takes advantage of this to prevent like repeated computation. So let's say you had, I don't know if you guys know about even functions. Even functions are functions whereby I think f of x is equal to f of minus x. Okay? They give you exactly the same value. An example of such is where all the powers of x have like square. Yeah. Or even powers. Have even powers. So for example, we can have a function f of x that is equal to x squared plus 3x raised to the power of 4. Right? In this case, if you pass f of a in here, you're going to get what? A squared plus 3a raised to the power of 4, right? And if you pass f of minus a, you're going to get minus a squared plus 3 into minus a raised to the power of 4. But anything raised to the negative sign raised to the power of an even power will get rid of that negative sign. So this is going to collapse down to what? Do you see that? We put 2 different values in f, but we got 2 different results. Does that make sense?
Sorry, you got the same result.
I mean the same result, sorry. So this means that if you wanted to evaluate a polynomial at 2 different places, but then you chose those 2 different values to be, one is positive, one is negative, then you only need to perform the evaluation once and then just copy the result to the next guy. Does that make sense? Yeah, no, assuming it is. So it's like you have a polynomial f of x. The goal is to evaluate this polynomial at 4 different points, like to blow it up, for example. But then evaluating is costly, right? Cost work to evaluate. So if you choose the points that you want to evaluate as as positive negative pairs, you can reduce that work. Assuming that this is like an even function, obviously. So let's say you choose a minus a, then b minus b, right? So you want to evaluate at 4 points. If this was not an even function, then you have to do evaluations for each and every single one of them, right? Which would mean like 4 evaluations. But now because of this is an even function, and it has that characteristics that f of a is equal to f of minus a, all you need to do is just evaluate a, evaluate b. Then you just duplicate the result. So you do f of a here, then you just copy it here, f of a also. Then you do f of b. Yeah, that's if the function is even.
How do you not determine the function is even?
We'll get there. We'll get there. This is not, don't take programmatically yet, oh. This is just theory, yeah. We're just touching different places. Does this make sense? Yeah, sorry. Right? So that way you have reduced the work of evaluating at 4 different places to just evaluating at 2 places. And that's what FFT does. So FFT, the goal of FFT is to convert from coefficient form to evaluation form. And I think IFFT is like vice versa, or I've mixed it up. But they go one way and they go the other way. And in order to do that, if you're going from coefficient form to evaluation form, you need to evaluate at d plus 1 point. So rather than doing like all d plus 1 points, you can evaluate at just half of those points based on like the even odd thing. Okay, so does root of unity make sense?
Yeah.
Does it make sense? Any questions?
So that's point where you convert I'm trying to make it make sense. From that point where like interpolate, you go and interpolate.
The polynomial, your original polynomial. This is what you're talking about.
So you interpolate in the next step. You interpolate the next step here polynomial. Then you now do it of using the parameters. What you're saying is that the points we're evaluating are
Roots of unity. Yeah.
But are we not supposed to get add just like powers of tau?
Powers of omega.
Yes, it's just like powers of tau.
Yeah, kind of. Yeah, you know that you can generate the entire root of unity set by just raising omega to 0 from 0 to n minus 1. I don't know if you get that. So what this is doing here is just like, it's just generating all the nth roots of unity. So all these values here are values such that if you raise them to the power of n, they will all give you 1. So if you do something like a dot map v, then v raised to the power of n, then dot collect or something, you're going to have a vector that has just everywhere. Does that make sense? Evaluating f of x. Yes. Yeah. So after you interpolate and get your polynomial, you are interpolating at the roots of unity. Yeah, evaluating at the roots of unity to get all the concrete values in this new code word. Make sense? So the interpolated set is just the roots of unity. It's the roots of unity. You know, every point is like x comma y, right? And all the x values are the interpolating sets. So it's basically like w0 comma y1 and w1 comma y2, no, not like that. Make sense?
And then you know the entire root of unity by based off of the blow up factor size and everything.
Exactly. Exactly. Make sense? So let's proceed.
Wait, sorry. That. What is the message they were calculating to get f of x?
The polynomial we're trying to commit to. But then, you know, the polynomial we're trying to commit to is a degree D polynomial, right? But then it's not that different from other degree D polynomials. You get? Like, without doing this blow up, what will happen is that the polynomial we're trying to commit to is like this, and then this is its own circle. And then the next polynomial we're trying to commit to is like this, and this is its own circle. So everything is so close, right? So the reason for doing the blow up is to now turn that into something that looks more like this. Adding more distance, but we're still keeping the degree.
What I'm confused about is that when you go,
Yeah.
what are we using to generate that f of x? So,
F of x itself is the polynomial we're trying to commit to. So let's say f of x was equal to 2x plus 1, right?
yeah.
Let's say we got it from
So this is the message. So now, what we now do next is we have the roots of unity, and we evaluate this polynomial at the roots of unity.
yeah.
Because from what you do, I thought you were calculating this x, y, w, and we were using it to get f of x.
No. And so you still get f of x. Like, they are all points on the same curve, right?
If they give you F, you don't need to calculate.
Yeah.
So what's going to happen is that you're going to have it like this, right? And then you just go straight using FFTs and IFFTs. Like, you're not supposed to do like regular Lagrange interpolation, but it's still the same conceptual. It's just that one is way faster than the other. Make sense? So message, code word. Cool? By the end of the day, everything is still the same polynomial. It's still message and code word still represent the same polynomial. Should we proceed? Okay, what do we do next? What do we do next? What do we do next? Okay, so now let's start talking about the folding a bit. This is where you guys need to be attentive. The folding step. So let me do it the way they did it in STAR 101, for example. So you have a function called f of x. F of x is a mixture of different terms, right? A constant term, then even terms, odd terms. So what they do is they say that f of x can be written another way. F of x can be written as f even of x squared plus x times f odd of x squared. This is another way to. So I will go into detail as to what f even is and what f odd is.
What does it represent?
This is representing the same polynomial. So like they are trying to write the polynomial. So this f of x is basically like your first code word, right? Now you're trying to write this as you're trying to write it based on like two different polynomials. And these two different polynomials should be of the same length. You can pad if it's not. But then
So we're trying to write that one with all the ones as two different polynomials.
not the code word.
Yeah,
It doesn't have all ones, and it's just I know I did a map and a collect. Yeah. Let me give an example. So let's say f of x is this, right? F of x is 3 plus 2x plus 5x squared plus 8x cubed. Okay? This is f of x. So what I want to do is want to break it down into two new polynomials. So what we do is that we collect all the even powers. Okay? Take it as like x raised to the power of 0, right? So 3x raised to the power of 0 and 5x raised to the power of 2 will go together. So we now have 3x raised to the power of 0 plus 5x raised to the power of 2. So this is like the even. Yes. Like when the power mod 2 is equal to 0. But when the power mod 2 is equals 1, we'll go to the other side. In this case, that's this one and this one, right? So 2x plus 8x cubed.
Why do you not put this in there?
Where?
That's what we want.
Where?
That's what we want. That's what we want.
Yeah, I'm coming to that. So the idea is to get even functions. Remember even function I studied that f of x is equal to f of minus x. So all the power should be 2 or multiples of 2. Right? That's the goal. So this one is yeah? F of x is the polynomial that represents code orders. Okay? Now to make this odd side the powers on multiples of 2's, what do? We can factorize out x. So this is like 3x raised to 0 plus 5x 2, then plus x into 2, right? Plus 8x. Yes, 2x raised to the power of 0. Right? So now both these sides are even functions. Meaning that you can evaluate them at 2 different values and you get the same output. You can evaluate at x and evaluate at minus x and you get the same output. So the only thing here is this other guy. But then they now change that to the verifier's randomness for folding. We'll get there. One step at a time.
What we are saying is, in that function, is f of x starts. What it makes is like powers of t. I mean,
So
two of powers of t.
no, there's a reason. I'm going to factorize out x squared from each of them to make them just like regular polynomials. So we're almost yeah. Okay, so now let's factorize out x squared from each of them. So let's call this now. So let's say our f even is going to be what? 3 plus 5x. Then our f odd is going to be 2 plus 8x. I removed it. Then, remember how we wrote our f of x? F of x is equal to what? F even of what? right? So now if we evaluate f even at x squared, so wherever there is an x, we change it to x squared, right? So that's now what? 3 plus, right? Right? Then we can multiply out. Then we can rearrange, right? Thank you. This is correct, right? Can you see this? And this should be exactly the same as what we had originally.
That F even.
Wait. One at a time, you see?
I can go from 3x 0
Yeah.
plus 5x squared to 3 plus 5x.
I factorized out x. It's like
But there's no x in 3.
I know, then that's just 3.
No, like the
I can
even,
do x from
like the even, F even, so
Eh.
25 plus. No, the F even, like what you wrote.
Yeah.
They're factorizing out there.
Like,
Zero by
this
X.
is supposed to be 3 plus 5x squared.
Zero by X plus 5X.
Why x? No, I'm removing.
X plus zero.
See. This is an even function.
No, like this F even now.
I know it. You're saying there should be a square there.
Yes.
I'm saying that I removed the square. Because this is how I'm using the f even. I'm passing in x squared to the f even. So wherever there's x, it will be replaced with x squared. So we'll be able to get back the original. So we created a new polynomial, 2 new polynomials that can help us get back the original polynomial. But then those 2 new polynomials are just like regular polynomials in their own right, in the sense that they have like x constant, x to the power 1. They're not all just even. I don't know if that makes sense. You're saying something?
It's just, what you explain what I'm just trying to say. It's like how you would think about that 3 plus 5x.
But
You
then,
already said it that way.
but then this concept that you did now, this you're supposed to do F even and F odd, but neither of them are either even or odd. So how do you? Because this way now you can take the F odd as F even, and you can take the F even as F odd.
Yes. It's just it's just a naming, right? The naming came from the way we split them up initially. Like the way we split them up initially was that we moved all the odd powers to one side and moved all the even powers to another side, right? And then that's where the even and odd is coming from. It's not necessarily that, oh, this is like an even powered polynomial, this is an odd powered polynomial. At this point it was still like even pairs, odd pairs. But then once we now factorized out the x, then that other side now became like an even function also, right? And then at that point we just like, this is not me, it's more like the way FRI is taught. They just call that side f even, f odd. But I think some people call it like g and h, which is fine too, right? So instead of f even of x, it's like g of x, and then the other one is h of x. So the entire this thing will just be like f of x is equal to g of x squared plus x times h of x squared.
My question now is, how are we able to factorize out X and really doesn't exist?
No, so it's not. I won't say factorize. Factorize is the wrong word. It's more like you want to,
Then you're increasing the variables.
yes, like you're trying to compose.
More like a different
Huh? Yeah, creating a different polynomial that can get you back to the original polynomial if you evaluate that x squared.
It's not like directly from factorizing out of one.
Yeah, it's not like we're removing x squared from. It's like composition. Like we're taking a compound poly and we're trying to like make it as a poly of police.
Something.
I think composition is the right word.
Yeah. Don't worry. Don't worry. And don't worry, Fry, there's a lot of videos on Fry. So when you're done here, there's still a lot. You'll see different perspectives. You just don't start looking at, yeah, you see different perspectives. But most of them now start going like very, very, like that. You know the video that we're talking about that we were watching for um, a couple hours, and when we looked at it, we were only like 4 minutes in. Yes, that was on Fry, but like by Dambone. So that one was going like to the depth in terms of like error correcting codes, Johnson bounds, minimum harming distance, the reason why fry is fry. Then there's stack 101 that teach you fry in like 5 minutes or 6 minutes.
So did you finish the reason why
Yeah, we finished that one. Yeah. So that shows you the level of, and when they taught that in like 5 minutes or 6 minutes, I said, oh yeah, implement. So that was enough to be able to implement it. But then they did not touch error correcting codes whatsoever. So Fry is like that. It has like different layers to it.
Can you spell it?
Cool.
No.
Oh. Let's say for Fry. I'll still send everything, sure. Except for Fry whiteboard or ZK hack. There are two videos, part one, part two. Okay. So let us proceed. So now that we are here, right? Now that we're here, this G and H are even functions, right? So that means that two values, we're trying to fold, don't forget. Two values, we're looking at the interpolating set now. Let's say this is W0, or let's call this A, just to make it easier, and minus A, right? If you evaluate G of x squared at A and H of x squared at A, you're going to get the same result as when you evaluate G of x squared at minus A and H of x squared at minus A. Does that make sense?
Sorry, come that's the given function.
Yes. So G of x, G and H of x, they have gotten rid of the distinction between A and minus A. Because of, before you pass it into G of x, you first of all what? Square it. Okay? So if I wanted to evaluate this at A, that would be G of A squared, right? Plus x times, so this is a key thing. That x, forget about it for now. That's going to be replaced with verifier's randomness. That's what will fold it. So it's like you're taking two halves and then you're folding it into one. Okay? So when I'm talking about x now, just look at let me even change it to, okay? So now, if I'm evaluating x, G of x squared, so regardless of whether x is positive or negative, the equation will look exactly the same, right? So let's say I wanted to do evaluation at A. That's going to be what? G of A squared plus R times H of, make sense? Then F of minus A, G of minus A squared. What is minus A squared? Do you see it? So now two values in the top give you exactly one value. That's the folding. So for every value there will always be another value that will give you exactly the same output. So you only need to write it once in the mm, both. uh,
Further, can you just
recap.
yes, further?
I'm coming. I'm trying to think of an alternative approach.
You're not recording.
No, I beg. Let's try different. So you had your original polynomial, right? Your original code word. That was the first one. Then let's assume that the interpolating set of this is okay, let's even use the roots of unity that we generated. What was the fourth root of unity? 1 minus 1 I minus I. What's the one we generated from the squaring? I deleted it. I'm not sure about this order, that's why. This thing is what? Minus I, right? That's the... So it's supposed to be like, the interpolating set is supposed to be minus I raised to the power of 0, right? Minus I raised to the power of 1, minus I raised to the power of 2, and minus I raised to the power of 3. Okay? Now you're going to fold it into something that has just 2. Yes. Now this thing is going to have a different interpolating set. That's omega. That's the fourth root of unity in the complex plane. You get? All of this, when you like get the powers, you get that. Let's actually do that. What is I raised to the power minus I raised to the power of 0? Then what is minus I raised to the power of 1? What is minus I raised to the power of 2? I?
No. I squared minus 1. Minus 1
Sorry,
times.
minus 1.
Minus 1 times minus. Okay, minus 1. Yeah.
You see? So they're exactly the same. So these are what interpolating set.
Are we raising to the power of 3 because of the
It's because of 4. It's like fourth root of unity, right? So that means that, and we have a generator, which is minus I. And also generate 4 points.
Say 4
Fourth root of unity.
truth of unity.
Fourth root.
Yeah.
Fourth root of unity. Right?
Okay, it's always 4 truth of unity.
No. In this case now, where my code word has just 4 elements. So the goal is that you want your interpolating set to be roots of unities. But since I'm going to be using 4 values, then I need to use the fourth root of unity.
I want to know where they fall. Why did you choose to use 4 values?
Just that's why I chose random. No, that's why I chose randomly. So like your code word is going to be a power of 2.
I thought maybe it's based on some polynomial.
Yeah, it's based on some polynomial. So I'm just assuming that after I did my blow up to my code word, it's just 4. But it could have been any other power of 2. So if it was 8 or 16 or 256, then you get like the 256th root of unity, which will give you omega. Then you can do omega raised to the power of 0, omega raised to the power of 1, up to omega raised to the power of 255. That will give you all the interpolating sets. And all those values, if you raise them to the power of 256, will give you 1. Cool? So now, what's the interpolating set for the new folded?
It should be
You square all of
yes,
you square them. So 1 square minus 1 square. That'll be 1 and minus 1. Because if you square the others, you still get the same.
Makes sense?
Yeah.
So the interpolating set there are 2 ways to get it. You could square all of this. So this is like something that when you square everything, it reduces. Because some of them are duplicated. But you can also get the second roots of unity. So there are 2 ways to get it. Because it's 2 values now. So if you square 1, that's 1, right?
Mm-hmm.
We have not seen that before. If you square minus I, that's minus 1. We have not seen that before also. Then if you square minus 1, that's 1. We have seen that already. And if you square I, that's minus 1. So this is the interpolating set. So this means that there is a polynomial that you evaluate at 1 to get what is here. And you evaluate at minus 1 to get what is here. But then this polynomial is related to this other polynomial. Okay? So now, if we know this polynomial, we need to be able to get this polynomial. That's the goal. So that we know how we fold. Folding is... I'm just trying to find a way to explain this folding process. Because it's really important. Okay, so we know this one is already f of x. And we said f of x is, let's say, g of x squared, right? Plus x times h of x squared. Now, before the prover can fold, it's going to ask the verifier for r. R is what it's going to use to fold. So it's going to replace that x with r.
How is R coming from?
It needs to fold. It needs to fold. So see the degree of this polynomial. That's another reason for the x square factorization. Remember that as you are folding, the degree is reducing. Remember. So that's why we need to also factorize out the x square so that the resulting g now has less powers. Remember in this case, you see here the degree was what? But then when we factorize, when we got like our f even, our f odd, after removing the x square, the degree is what? Then when we now multiply by r and add, the degree will still be 1. Does that make sense? Let's say r is 5, right? So that will be 3 plus 5x, then plus 5 times 2 plus 8x. Can you see it? After folding, we now have a degree 1 poly coming from a degree 3 poly. We started with a degree 3 poly. Then we split it into even odds. Then we now remove the x square, because it doesn't matter anymore, right? We'll have x and minus x. Yeah.
So I'm guessing in the after the folding is done, we can go back. We can
Yes, you can relate two of them. You can't. Yes, kind of. You can relate it to do consistency checks. But you can know if the smaller one was gotten correctly from the bigger one. And that's what we're trying to get to. But this is somewhat complicated to explain. But you can know if the smaller one was gotten correctly from the bigger one. That's how you check that the folding was done correctly. So it's like, we can call this one f0 of x.
Can I see that one where you wrote R?
So the folded polynomial is basically g of x
Why is the x this time? X squared.
because the interpolated set has already been squared.
It's just us like.
No. At the end of the day, it's still with g of, how do I put it? Like going down.
Yeah.
But now I'm trying to do from here to here, not from here to down. I'm trying to show you how you can get the values here based on the g even and the g odd that you got in the previous step. You get? But then the square has already been done like implicitly, right? So technically it's like still x square
Yeah.
when you're talking about x from here. But now when you're just looking at x from
This
here,
is-
then you just put it in there. Okay? So now at the end of the day, like after you have folded those two polynomials, you're going to have a new polynomial that is now of less degree. So this is the new polynomial, right? So initially we started with f0 of x, which let's say had degree 4. In our case, I think we had degree 3, right? Because this was our f0 of x. Where is it? This, right here. Okay? Then after we folded, we got what? Which is degree 1. Okay? Then you can do the same thing again. Even powers, odd powers. Yeah, for the even side you get a constant. Then for the odd side you're going to get 45x, right? And you factor out x squared again. In this case, like there's no x squared per se. The point of folding is to get a new polynomial that has yes, a new code word that has less half of the degree. I want to continue doing this until you get to something small enough that the verifier can just interpolate and check that the degree is actually
But there's something small enough to be a constant.
could be a constant, yes, or like two constants.
Two
It depends.
constants.
Yes. And you could stop here, right, at degree 1. And then something small enough is just 13 and 45, right? Or you could fold even more to get like a single constant. Because when you fold, it's like 13 plus x times 45, right? This x will be replaced with r. So that will now be like a value and just a constant. So you could go down there to stop at degree 1 and then another.
So the folding, that's when we use the F even and F odd to do.
So you take the big code word polynomial, you split it into two smaller polynomials, then you remove x squared so that their degree reduces, right? Because the x squared is still there, then one of them will still have like x to the high power shall because of that x in front. So you remove that, then the degree has reduced, and then you now multiply randomly linear you do a random linear combination based on that r that is there. So you combine the first half and the second half.
So like you're saying that in polynomial has an even side.
Yes, up polynomial have an every side.
And then we're removing the x square at first because we are assuming that it's going to be degree 2.
It's because first of all there are two reasons, right? One is that we want to make the problem, it's divide and conquer. So you start with a big problem and then you reduce it to a smaller problem of the same form. And then the smaller problem in this case is that the degree has halved, right? That's what the x squared is kind of like doing. It's like halving the degree. But now, I'll just say something else. There's another reason, which is like, the roots of unity. X squared is fine because there are two values that will give you exactly the same x squared.
No, I didn't get that.
So like roots of unity, there are always two values that will give you the same when you square them. They'll give you the same value.
So like in this example, the highest power of x was
3,
x
right?
cubed.
Yes.
What if it was x raised to power 6 or something like that? Will
You
it
still
start
do.
with x squared?
Yeah, you still factorize on x squared. So like an example is like f of x is equal to 5 plus 6x squared plus 8x cubed plus 9x raised to the power of 4 plus let's say 15x raised to the power of let's say 6. Alright? So we'll do the even odd split again. So what you're supposed to do is that you're supposed to, for the things that are not there, you have a 0. So like if there's no x5, right? And that's like plus 0x5, for example. So now if you are splitting this, the f that will be 5 plus what? There's also plus like 0x1, right?
But 5x raised to power 0.
Yeah, 5x is plus 0. I'm just making that implicit. Does it make sense? So this is an even function in the sense that if you're passing a and you're passing minus a, it will always give you the same output. Then you now do plus, The odd side, that's what? 0x1
plus x3 plus 0x1.
That's alright.
Right?
Okay. But then we can factorize out x to make that side also an even function. So it's like 5 plus 6x squared plus 9x4 plus 15x6, then plus x into. I'm just going to get rid of the zeros, okay? So just 8x, right? So this is supposed to be like our polynomial for our f even, but without the x squared, right? So I've not yet reduced the work. Because if we just fold like that, we'll still have raised to the power of 6 in there, right? Because it will be like r times this, which will just change the 8. But then when we add it, we're still a degree 6 or a degree 7 polynomial. So because we're doing divide and conquer, we need to make sure that the problem is getting smaller every single time. In this case, the degree of the polynomial that is creating the next code word has to have a smaller degree, half the degree of the previous one. But then it is fine to do this because of we're working with the roots of unity, right? It's fine to factorize it out because we're working with the roots of unity in the sense that whether you pass in a or minus a, you're going to get the same value. So there are always two values that when you square them, they give you the same thing. Because you want the domain to also reduce, that's the interpolating set to also halve, yeah. And roots of unity give you that. Like you just square the old interpolating set, and you're going to get a reduced interpolating set. So our f even is going to be what? 5
I think it would be less confusing if we can just exchange this x one that now it looks like a then f of
let me call
then
this
f of a or something.
let me call this g of x.
So isn't that like we're dividing all the even powers by 2?
Exactly.
Alright.
Like with, she just said that it's like you're dividing all the powers by 2.
Except the first one.
Even the rest first one, like 0 divided by 2 is still 0, which is still 1. Yeah, the powers. Yeah. The goal is that you shall want a. This is an even polynomial. Everything is just square, 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 square. Multiples of 2. What you're trying to do, you're trying to get like a regular looking polynomial that is like constant power of 1, power of 2, power of 3. Regular looking. That's the way you would divide the domain or the degree in half. Then for the other one,
Okay.
that's 8x. Right? So your folded polynomial is now going to be g of x plus r times h of x. This is the polynomial that we're going to use to generate the next code word. Yes. This one was what you used to generate the first code word, right? That long one. Now this one, once you have finalized this is the one that you're going to use to generate the next. But it's fine, right? Because the degree is smaller. So you don't need as many points anymore to be able to represent it. Sorry.
Why is R only multiplying the check?
Because r just replace x here.
That means you're not factorizing the even side.
There's no need to because it's already like squares. So the only reason why I was doing that because that side is like odds.
Yeah.
So I want to make it also squares.
Okay.
so that it's good for like root of unity, because root of unity likes even functions. Because what we want is that two things give one. That's the goal. Two things give one. So as we have removed that r, then let's say this is the first thing. Then there's another thing here that also gives that same value. That's the goal. Want two to give one. That's how you reduce something of size 8 to something of size 4. But since your g of x and your h of x are like even, then that happens.
And what for the fold?
Yes, you can further fold.
Yes.
Let's do it, yeah. So, it's still writing.
When you talk about that projected f of x equals to g of x squared,
Yes.
g of x squared.
So you want to express,
In this case now, g of x doesn't stop at square. It's also g.
yeah, but you can evaluate it with x squared. So evaluate this with x squared, then wherever you see x, you put x squared, right? Evaluation is just which will not give you back the original one. So there's a way to express the top polynomial in terms of these two smaller polynomials. That's how we'll be able to do our consistency checks.
So we get to get g of x, so you can put that in x.
Yes. You need to get g of x, you need to get h of x. Then use those to fold to get the new thing. So let's fold fully. So what should we do as our r? Let's give me a random r. So the polynomial for the next code word, let's call it f2, is going to be what?
X is our R.
The x.
Now R.
Yeah, that x is now our r. This will be replaced with r from the verifier. So what's the folded result? That's 5 plus 6x. That's this side. Then we're now going to do 3 times this other side. Right? But you can collect like terms. So this is the polynomial that we're going to use to generate the next code word, right? But now the interpolating set is different. It's the square of the interpolating set of the top guy. Remember we did this, right? So this was when we had our first f of x, we evaluated that at 1 minus I minus 1 and I, right? Then after folding, we're going to get a new polynomial, but this polynomial are only going to evaluate at 1 and minus 1, which will give us this 2.
Sorry. Hold on. Let me see what you did in that. That's 3 times 2x. That was
Yes,
that give to
24x.
24x.
Yes,
So you're not adding 24x to 6x.
yes,
To give 30x.
yes,
That's the only place that.
yes.
So this f2x, what is it called? Is it like?
It's in polynomial for the next. So there's an associated polynomial for this one, this f1 of x, and there's an associated polynomial for this one, which is f2 of x. So
Okay, so if you want to for that fold, is this f2 of x that we use to
exactly,
fold down?
exactly.
Alright.
So let's do that now. Okay.
Why does 6x squared reduce to 6x squared? 9x 4 9x 4.
So she gave an algorithm. You divide the power of x by 2. That's how you know the new power of x.
Yeah, I get that, but like you said that when you're like everywhere you see x, you use x squared.
Like if you evaluate at x squared, right?
Mm.
You evaluate g of x at x squared. So if you evaluate g of x at x squared, that's 5, right? then plus 6x squared, right?
That's
I'm
nice.
replacing the x.
Okay.
You know, evaluation is just wherever you see x, replace it with whatever is in here, right?
Okay.
So x there is now like x squared. And for the other one, it's like 9x. X is x squared, right?
X
But that
squared
x raised to the power of 2. So that would be like 2 times 2, which is 4, right? Then plus 15x squared raised to the power of 3, right? So at the end of the day, it's what? 5 plus 6x squared plus 9x4 plus 15x 6. Make sense? Except,
Let's just get back the original problem.
yeah,
Okay.
I was showing how if you were the x squared. Make sense? So
Yeah.
now let's do further folding. So we have our F2 now.
Yeah, but this one, what is the original polynomial?
The original polynomial was this, the one I circled. Okay?
So this is X,
F1 of x or F0, yeah. This was the first one. This is one that we used to generate the first code word by evaluating it at all the roots of unity of that first code word size. Then we folded this into a new F. Then we're going to evaluate that the half, the next root of unity, which you can get by just squaring the top roots of unity. But then there will be duplicates, so it will reduce into half.
Where did you evaluate this?
We never like evaluated it, but it's just like that's what gave us. You get.
Okay, that's what the f of x want to start with.
So the f of x came from that's the polynomial we're trying to commit to with FRI. Okay. Now that polynomial can be evaluated expressed in evaluation form, right? But that evaluation form will be much smaller than the code word, which is this. So what we did was that we interpolated or we just took that, and then we now got this, then we evaluated at more points. So evaluating that first polynomial, this one, at all let's say this was like 16 points, at the 16th root of unity is what's going to give you this array of like values. Okay? Then we'll now take that polynomial and fold it. Then when we fold this, we're going to get a new polynomial that we can now evaluate at all the n minus 1 roots of unity.
Sorry, can we change variables?
Why do you want to change variables?
No, like, it kind of makes sense.
To change variables.
Yeah, like,
What variable do you want to change?
because now you know it, you first have f1 of x,
Yes.
right? Then we want to now equate it to something like equals to g of a plus x h of a. Then
But that a now, how is it related to the input? Where does a, like I want to evaluate f of x. You know, I'm supposed to distribute it into all.
So it not be like a is equal to x squared.
And you can do a is equal to x squared.
Yeah.
But why do you?
Because it makes it easy because so now you're not saying we change x to r, right?
We changed.
Yeah, we change x to r.
Yes, that x particularly, right?
Yeah, change
We
to
changed
r.
to r.
But we did not touch x squares.
No, we didn't.
So it's the same thing as saying we'll say x squares not become a.
But the thing now is like, it's more like from that polynomial we just got our g of x and our h of x, right? Then we just merge them by doing a scalar mole of h of x, then plus g of x, and by r. So it's not like as if we're like going back to touch that other equation. It's more like from the first f of x, we got two smaller polynomials, and then we just merge them together.
Yeah, you do that. It's confusing when we're able to change
Just
x, and it's like you are saying substitute.
I'm more confused if you change the variable.
Like you are saying substitute x R as X. But we're not substituting everywhere. We're not skipping X here.
So that's why I'm trying to explain that. Don't think of it as substitute R for X. Think of it as merge two different polynomials, g of x, and so think of it as like this, like you have f1 of x, right? From this f1 of x, get two new, that's the first step, get two new polynomials, g of x and h of x.
Okay.
When you have gotten these two, ask the verifier for r, for some randomness that you use to merge these two polynomials together. Now the verifier is going to give you r, and then you're now going to do g of x plus r times h of x.
Sorry.
So don't try not to link it too much with like the, oh, we're substituting x, but we're not substituting it here. It's more like we just got two polynomials, and then we merge them with r.
So because I was thinking of like if we get to the bottom,
Yes.
and then we'll now say okay, substitute. If substitute.
So is this more like to get the R?
Yes.
You basically have to copy the order and then
Comment like transcript.
forget one. I want to say yes, but like, so what prompts giving you the R? The verifier giving you the R?
So once the first one has been generated, it's going to make a commit.
I remember.
Then send that make commitment to the verifier. Then the verifier will reply with R. Okay?
Yeah, sure.
Let's do the next one. Okay. Yeah. Yeah, based on the size of the code word, which is defined by the graph factor and the message. Eight. Roots of unit. Yes.
Now evaluating that polynomial as we put 8 root of unity, we're going to put all of the values, right?
Yeah, you're going to get all the 8 roots of unity. Because you just use like, you just get the first one, which is generator. Then you raise to power 0, raise to power 1, raise to power 2, up to 7. Yes. Then you now have like different values for your x. Then what you now need to do is evaluate that your polynomial at all those different values of x. This is assuming you are doing like Lagrange interpolation and evaluation. But with FFTs, everything is kind of like done automatically.
So the generator raised to the power of the
Indexes.
like your x values,
Exactly.
evaluate the polynomial.
Yes. So now get your actual code word. Then once you get that code word, you commit to it using a Merkle tree. You send that commitment to the verifier. The verifier will send you the randomness that you use to now get your next code word. Okay? So now, let's continue. So we had this polynomial. We used that to generate a code word. We had a polynomial. We used that to generate a code word. After generating the code word, we Merkle committed, sent the Merkle root, verifier sent R. We then used R to fold this into a new F. How did we fold? We got G of X from this. We got H of X from this. Right? This is our G of X, this is our H of X. Then we now merge the two of them using the R that the verifier has sent. In this case, R was 3. And then when we merged it, we got to this 5 plus 30x plus 9x squared plus 15x cubed, right? Which is a new polynomial of degree 3, while the initial polynomial was of degree 6, okay? So it's already half. So now that we have this new polynomial, what does the prover do? the paper will use that to generate the next code word, right? By evaluating it at the roots of unity for this, which you can get from
feel like they all have the same concepts, kind of.
what and what.
Everything, like, because when you fold, like you fold, the verifier will definitely give you a random time.
Yeah, you're just doing the same thing. Yeah.
You do the same thing.
Yeah.
At the end of the day, you still get the final value.
Yeah.
Basically, would be like, let's say,
Constant
final
or
EM or
two.
something, which the verifier will also check on their end.
Yeah. Oh, you're relating to like some check, are we?
Yeah, not reasoning assumption. I just mean everything is almost using the same principle of if you check some check, random challenge, GKR, random challenge, here too, the verifier will still generate randomness, and at the end of the day, they're just folding to something that the verifier will verify.
Well, okay. So what you now need to do, the next step is now learn like 30 proof systems, right? I'm just like learn a lot of proof systems, then try and see.
The differences.
Yeah, so there's going to be like an essence. Yes, there's a core. Me too, I'm still looking for that core. But I've been seeing, so there's an essence, the thing that really makes this thing work. Because all of these are like variations of that essence. So the more you like study, the more you start seeing that core. Like there's a very clean relationship between FRI and some check. Like there's a very, even, so base fold, which is like multilinear polynomial continuous scheme that uses FRI, it uses FRI and some check, and it's doing two of them in parallel, and they're all using the same randomness. So the guys that wrote that paper must have understood the core relationship between some check and FRI. That's how they were able to see that connection. So this is why like you need to study at depth and then try and like connect. But it's good that you're seeing those kind of connections. Yeah, the five people. I will not. You can try, but it's very not recommended.
Can we use the root hash?
Yeah?
Can we use the root hash as
Mm.
our
They use it technically, right, by putting it to the transcript.
okay.
Technically. But I don't know how safe it will be to just. I guess you're just saying that convert it straight away to like a field element, right?
Yeah, I use it.
I don't know how safe that will be. I don't have the tools
So you
to
still
ascertain
commit,
that.
like, you still commit it.
They will still commit it.
Just click on that one.
You still commit it. But the good thing is, the transcript now is like the entire history is tied, yeah, it's linked. But if you just use it like that, then it's just connected to just this here. Okay. Should we continue? So, f2 of x, we have already generated our code word from that, and we have done our Merkle commitment, and we have sent it over, right? Now the verifier has sent us another R. Let's say the R is what? 5, right? So now we have to do the same thing. We need to get g of x and h of x. Then we merge two of them based on r equals 5. Cool? So g of x are the ones with the even powers, right? So that'll be 5, 9x squared. Those are the even. Then plus what?
30x plus 10.
Is it 15 cube or 15x cube? Why did I write cube here? Okay. Plus 15x cube, right? Then we'll factorize out x from the odd side. So they are both even functions. Yeah?
Yeah, I wanted to know, like, this whole verifier sending randomness, right? You know, when we're doing GCAR and something and all of that, there's always a prover and a verifier communicating, and we now have to use the transcript to do the verifier part of it. Now, we are still introducing the person doing this is the approval, right? And we still have a verifier that will be sending randomness again. So are we still going to be using transcript to make it known it's a happy? So it's the same thing.
So you're using transcripts. So anytime, like every time the prover commits, does the make commitment and gets the root hash, it's supposed to send that over. So instead of sending it over, you're going to write it to the transcript. Then anytime the verifier is supposed to send you R, you squeeze from the transcript. Same idea. All right. So,
Sorry, so it's quite but I kind of need to reiterate what you said, where there is a polynomial that gets converted into like a code word, and that code word gets converted into
another code word.
by using the folded.
Yeah, that one gets into another code word. And then you're just continuing that process until you get a very tiny code word.
Then you have to code word to code word to code word to code word.
Until maybe like you have constant. Make sense? Okay. So at this point, we have the ingredients for our g of x and our h of x. We just need to factorize out x squared from both sides, right? So what is our g of x?
X 5 plus 9
Make sense?
yeah,
Then our h of x is what?
30 plus 15.
Cool?
Yeah.
Then we can now merge them based on the r. So it's going to be, yeah.
Do you have the x cube of your vector?
I didn't add it. Oh, okay, thank you. So yeah. Make sense?
We are folding.
Yes, I'm following you.
Where is the 15x cube coming from? I thought we
From-
already deal with that.
From the last fold.
Sorry.
So let's reiterate, right?
Okay. Okay, from 15x principal of 6.
Yes.
Okay.
When we factorize out the x squared to get our g of x,
Okay.
it now turns to like q.
Okay. X squared.
Yes.
Okay. Times 2.
Yes. Then the other one was x squared. It turned into 8x.
Yeah.
Make sense?
Yeah.
So that's how we got this plus 15x cubed. Then now we're trying to fold that so that we can get the next polynomial, to get the next code word, to get the next Meko root hash. Yeah, listen.
What are you doing? If it's roots of unity, this thing, guy, like, and at this point, so for all we are doing is just, I don't know.
So when you get the polynomial,
Yes.
to get the code word,
Yeah.
you evaluate that polynomial at all the roots of unity.
Okay.
Then once you evaluate all the roots of unity, you now have like an array of field elements. Then you now do a Meko commitment of that array
Okay.
to get the root hash. Then the root hash you send to the verifier. Verifier is going to send you the randomness they are going to use for the next fold.
So you send this to the right.
The root hash.
The root hash of this.
Yes.
Of the evaluation of this and
Yes. As the leaves. So this serves as the leaves of the Meko tree.
Okay. And this is that one you get from the 111 collect.
What's 111? Okay. You know, you're evaluating it at W0, W1, W2, up to W n minus 1. Now you can get these W's from this other one, right? Let's say W10, W12, W11, sorry, W12, all the way to W1n, a different n, right? The way you can get this, you can get this from, the way you can get this from this, right, is by squaring everything at the top and removing duplicates. Okay? So there are going to be two things here. That's why I marked here and there. Such that when you square this and you square that, you are going to get is similar to what we did. What do we do here? So this could be like the roots of unity for the top, that big one, right? So if we square this and we square this, we're going to get 1. So by squaring everything and removing duplicates, we're going to get a smaller domain, half the domain, or a smaller interpolating set. Then that's what we're going to use to evaluate the that folded one for that layer. That makes sense? It's getting clearer. Alright. Okay. So R is 5, right? And they're both same powers now. So we know we came from degree 3. Talking about degree 3.
So do you get the R is always different for you?
It depends on what the
Depends on what you verify.
so yeah. So the verifier is like flipping a coin. So it's public coin. Alright. So what do we do now? We multiply H by R, right? Which is 5. So that's 5 plus 9x, then plus 5 into 30 plus 15x, right? 5 plus 9x plus, what's this, 15? 150? Plus 20, 25, 45? 75, sorry. Right? When we collect like terms, that's what? Plus. Now this is representing our F.
So, you mentioned when we can represent all this in
Coefficient.
acceleration form.
No.
So it has to be in evaluation.
Everything is evaluation form. Everything. But it's easy.
So what did we pick as our new R?
We pick 5. Thank you. Thank you. Is that?
So these are unique polynomials. You're showing the evaluation with the root of unity.
Yes. So, yes. So I think at the beginning you do one FFT to get the evaluation form representation. But all the foldings are just using the evaluation form. Like, you just like, how do they put it? You to get the even and odd side, all you're doing is you take this one, like you create 2 arrays. You take this one and move it here. How do I put it? So let's say you had the array like A, B, C, D. This represented your evaluation form, right? What you're going to do to get your G is just take A and C, and to get your H, you take B and D. It's simpler. This is literally your G of X, and that's your, and it has already removed the X square for you. Because of, this was A with X raised to the power of 0, right? B with X raised to the power of 1, C with X raised to the power of 2, and D with X raised to the power of 3. By the time you move it here, this is X raised to the power of 0, X raised to the power of 1. This is also X raised to the power of 0, X raised to the power of 1. It has removed that X square for you. You get? Hmm? Someone asked a question.
How do you remove it?
It removed it for you by just like interleaving. So like the index is the power. So x raised to the power of 0, x raised to the power of 1, x raised to the power of 2, x raised to the power of 3, right? So this thing that I've written here is the same thing as
See, so 9x
is A. Okay, yes, exactly. Bx, right?
But this is for your like invariant.
Yeah. It's FRI is a univariate polynomial complement scheme in evaluation form.
Oh, okay.
Or in coefficient form. Yeah.
Coefficient form.
Yeah.
Okay.
So when you now interleave it, right? Normally, if we're doing it by hand, it would have been A x raised to the power of 0, right? Plus C x raised to the power of 2, right? Then after we'll now have to like remove the x square. So it will be a plus what? C x. That is already here. Like it's already a given just based on that. And it's here also. But let's focus on how FRI works itself. Okay?
But so far, all these things we've been doing so far, we've been skipping the whole thing about the roots and whatever. We're just assuming what R is.
What do you mean? Assuming what R?
Like, you know how you said that, like, you have a polynomial, and then you get, like, a, what do you call it, omega array kind of evaluated as, blah, 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 and then pass that to the verifier, and the verifier would squeeze us a random value.
We're passing the macro root hash,
That's gotten from this omega.
evaluating the polynomial at all the omegas. Yes, then
Get, commit that, pass
Yes.
that hash to the verifier.
yes. And verifier will squeeze. Yes.
And then
Transcript.
my question now is, this thing we are doing so far now, right? We're not taking cognizance of the omega. We're just assuming what the random value from R is. I don't know if that makes sense.
I don't know how
Obviously,
you're relating omega and R. So with omega, right? We're assuming that we know omega based on the size of the code word,
Yeah.
right? So if the size of the code word is 16, then we know it's going to be based on the 16th root of unity. The size of the code word is 8 to be the 8th root of unity, or nothing like that. So that's one.
Yeah.
Then R, we get it from the verifier.
No, I'm not thinking of like, I don't know if I'm trying to get like, it's, I feel like what we are doing feels like some kind of concerns where it's a polynomial that we have, and then that polynomial will be evaluated as the root of unity, right?
Yeah.
Committed to a
Macro,
tree,
yeah.
get the root hash,
Yeah.
pass that root hash to
The verifier. Yeah.
Verifier gives us
R.
an R.
Yeah.
Now that R, that we have that R now.
Yeah.
That initial polynomial.
Yeah.
We now do this.
Break it.
This,
Yeah.
And now evaluate it with that R.
You do the split,
The split.
then use the R to merge the two, yes, to get a new F.
Yes.
Then you now evaluate that F
Yes.
at the next roots of unity.
Yes. But I'm saying all this thing that, like, how do I explain what I'm saying? What we're doing here right now
Yeah.
does not necessarily involve the roots of unity yet.
We're just assuming that.
Assuming what R is like.
Not what R. Wait, why are you linking R and roots of unity?
No, because you get R. Whether you got to the roots of unity, done the root hash, got to the verifier.
And you were assuming, like I'll just ask you guys to give me R.
Yeah,
Is that what you're saying?
Yeah.
I'll just ask you guys to give
There's
me R.
later that maybe on the previous side I will not try and do.
Continue, no, finish it.
So on the previous side I will not try and get the roots of unity, get the macro roots.
Yeah. All the verifier is doing is that, from the verifier's perspective, in this phase, he just gets a root hash. It's a root hash. He just gets a root hash, and he just gives R. Gets root hash R in the commitment phase. So there's not another phase where we're now going to start checking for like consistency. Right now we're just doing forwarding. So the proof for FRI is that the prover would root hash, fold, root hash, fold, root hash until it has stopped folding. So the proof is just all those root hashes. That's the proof. That's the commitment, sorry, not the proof. That's the commitment. It's committing to the polynomial, yeah? To reduce, the point of FRI is to ensure that the degree is bounded. The point of folding is to ensure that you get the problem to a small enough problem that the verifier can check the degree by itself. Okay? So, this could be like a degree 1 million or degree 40. To check is by interpolating, right? And then checking the actual degree. But then for this one, it's too big for the verifier to do by itself. So you fold it to make it a smaller problem. So this was degree 20, this is now degree 10. Then you continue that folding process until you get to something like degree 1. Now that's small enough that the verifier can just like do by itself and check that it is degree 1. But then it's not enough. You need to now also prove that you did all the folding correctly. Because right now the verifier does not see how the prover is doing the folding. All the verifier sees is that you gave me a root hash and I gave you R. Then you went your way and you did your folding, however you did it. And then you now came to me and said, this is my next root hash. So like nothing the verifier is seeing proves that the prover has done the folding correctly. So that's where consistency checks now come in. In the sense that after you have now told me that, okay, I folded correctly, and these are all my root hashes, now you cannot lie when I ask you a question. So when I now ask you a question that will allow me know whether you folded correctly, when you give me your reply, you also have to give me like a MECO proof. So that way, I'm sure that the thing you committed to is what you're answering with. You get? But we're getting there. Making sense?
Yeah. So the first polynomial is
Yes. The first polynomial is the polynomial I'm commencing to. So that's the one that you use to generate the first code word. Then you now fold. Cool?
code of order folding, right?
Yeah, code of order. So you take a polynomial, you encode it as a code word, and then you just fold it.
Can you walk through how to evaluate the unit of
It's just regular evaluation.
like for let's say there are four we're using the fourth group.
Yeah, so like that I, 1 minus I minus 1 and I, that will be your X. So you have there's like universal polynomial that evaluates. So you just say universal polynomial that evaluates 1, then to give you another field element. The universal polynomial that evaluates 2. So you just like wherever you see X, you replace it with the current one that you're looking at. Then
And that would be
raised to power 0 raised to power 1 all squared. You get.
no,
Like if you
that's
had like 2x squared plus 2,
okay.
then you're evaluating f of x. So if you want to evaluate f of, let's say like minus I, that will be 2 times minus I squared plus 2. It's just regular evaluation. But you won't do it like this. You use FFTs. Like there's a reason why we're choosing roots of unity, is to use FFTs. Because FFTs, evaluation is like n squared. That's the running time for evaluation. So we are trying to evaluate like evaluation is n, right? But you're trying to do n evaluations. So like to evaluate just this guy, it's going to take me order of n steps. But I'm trying to now evaluate n guys, right? So if each one is taking me order of n, then n will take me order of n squared, right? So if I want to do this evaluation, it's going to take me order of n squared. But then with FFT, you're going to have order of n log n. And n log n grows much slower than n squared. So using FFTs is faster. Then some check multilinear, all those base provers don't even like do interpolation at all. So there's no need for all this O of n log n, n squared, especially with things like GKR, because like the entire proof system can be like O of n. Yeah.
Yeah. When you say using FFT, because literally the working steps minus the commitment and the hashing and stuff is almost similar to FFT working process. Even to the last bit where you have to now take the last the constant and the thing, then put it in a loop so it runs and stuff like that. I think the real difference is the omega and the R, where in FFT we use the omega, and for this one now we're using R for
Merging the two,
challenge and
yeah.
stuff. So now when you now say we're using FFT, now are you saying we're using FFT to anytime we want to evaluate or anytime we want to, or we are using that same syntax of FFT to just like the way you've explained it now? We're just going to write it in the syntax of FFT.
No, you
or is
use
FFT's evaluation and stuff that we're going to be calling?
yeah, you're going to call at the first step. That point where you're going from message to your first code word, you are using FFT for that process. You know, you start with a polynomial
Yes.
and then you blow it up,
Yes.
called Reed-Solomon encoding.
Yes.
So that Reed-Solomon encoding, there's a naive way, which is interpolate and evaluate over the roots of unity. So now get that
No.
blown up. But how you should actually do it is using FFTs. So Solomon is like, so you use FFTs to now like do the blow up.
Is it
Basically.
because the evaluation is sorry, the interpretation and evaluation computation is basically expensive.
Yes.
So you want to use FFT to basically convert
From
this
coefficients to
yeah
to
in lesser
evaluation
time
in
and
lesser
like,
time.
okay.
Yes. You get. So using FFTs to get that initial code word. But once you have that initial code word, then you just start folding. Make sense?
Yeah.
So that's where FFT comes to play.
Yes, just at the top. Cool?
And from there it's just the fold
It's just the
down
fold.
and
Cool?
Sorry. We are folding. When we fold, okay, we are going to wait. Why did you say we use FFT for again? You say
For the Solomon encoding, to get the first code word.
to get the first code word. Just there. But so that would mean that we already have the polynomial encryption form.
For example, exactly. Because
So-
FFT is like, you can take it from creation form to evaluation form, and can take it from evaluation form back to creation form. That's IFFT and FFT.
Okay.
So, if you have polynomial in creation form, you just move it to evaluation form, but over like a large
right.
root of unity.
So FFT does that.
Yes.
Yeah.
Then you get your first code word.
Okay.
Then you now split it into half, which will already give you like your g of x, your h of x. Then you
Mhm.
give it the r, then you just do scalar more, and then
Does that-
elements wise summation, and then you just continue like that.
Does that mean that FFT evaluation, not interpolation?
Same, and yes, kind of. Like if you started with coefficients, right?
Yes.
Then you just, yeah. But the point is that you have a polynomial and you want to evaluate at a lot of points. Yes. That's like, the end result is that you should have like a code word that evaluates that polynomial, which could have been represented in coefficient or evaluation, at a bunch of points, which is based on the root of unity and the block factor.
Okay, you know when we get the g of x and h of x, we're still going to evaluate it.
But you already have your code word.
Okay.
So it already has the evaluation.
Inside the code word.
Yes.
No, we're still going to evaluate it at the
Next set of it. But I'm saying that you already have those evaluations, kind of, based on
You
the
don't need to
previous
evaluate
code
it.
word.
They're basically
They're just folding.
So we won't really evaluate.
They're just folding. You're evaluating the first time to get the first code word.
Uh-huh.
Then once you have done that, you now split it. That interleaving step that I talked about. Where did I draw that? It's on this.
Oh.
So A and C, those are like the even powers. Then B and D, those are like the odd powers.
Okay.
Then you now fold. So that's like your G of X and your H of X.
So we're just taking
Those
one
two.
one.
Yeah, you stick like everything at an even index,
Uh-huh.
you push it into one array.
Okay.
Then everything at an odd index, you push it into
Okay.
another array.
Okay. So that is g of x, h of x. But then we will. I thought we still need to evaluate as powers of unity.
I feel like it's already done for you, like
Mm.
automatically.
since
Sorry.
the
Like once you merge it.
since the first encoding right has like all the possible points that would have evaluated that that's the way we put it. So that means every other thing is going to be based off that like first various points because you are squaring to get the next point where the next point goes.
Yeah.
Sorry, when you say FFT, you use FFT. Like you mean FFT, not IFFT, right?
I don't know which one. I always mix them up, but depending on, you should know like, okay, maybe FFT gives you coefficient to evaluation. So what do I have? And I'm trying to get to coefficient. So you just choose what you want to use. Within that. I don't know which one. I always mix. I don't know whether FFT is going this way or
This
FFT is
way.
going this way. It's always like, I always forget about it. But don't worry. If you guys want to implement it, as you're trying it, you start to see details. That's like implementation details. and then we'll just like trash it out. Okay?
That is a 50.
No, let's say FRI.
Okay.
We'll still do FFT.
But if you have like already existing FFT, you can plug it in when you're doing your solution.
Yeah. Okay, does this make sense?
Yeah.
155 plus 84 x.
Is it 84 14?
Is 84.
I believe it's
75 plus 9.
75. Oh, that's 15.
Yeah. 15 and 5. This is not S1.
Like this.
I don't know how to write 5. Well, yeah. So this is F3. Then we do the same thing. We know we're doing equation form, right? So we get the, evaluate this at the next roots of unity, right? Which we get by squaring the last one. So we're now going to get like a new, smaller code word. This one now is like degree 1, right? And then we do the Merkle commitment. Then we send that over to the verifier. Then we continue on to the last step where it's small enough. Once it's small enough, you don't need to Merkle commit again. So like both the program and verifier would have agreed that once the degree bound is, let's say, degree 1 or degree 0, you don't need to Merkle commit again. Just send me that code word directly. So that me, on my end, I will now like interpolate it and check that it is indeed based on that degree bound. Does it make sense?
How is it?
Let me see what.
What's an example of that?
Okay.
So I think that the verifier is not checking for the value of the degree.
Checking for the degree.
So in case you are like the wrong value now, it's going to take the degree.
That's like you give him a wrong.
Maybe you have like a 3.
It's okay. It's 3 instead of it's 4.
And
So that means that you folded incorrectly, right? At some point in your folding, you made a mistake, or you maliciously, yes. So at that point, the degree check is not checking for the values; it's just checking for the degree. But then there's now the consistency check. So the consistency check is going to check that all the foldings were done correctly. So at that, so there's a theoretical way to do it. Then you will now use the Merkle. So it's like the verifier is going to make queries. It's going to say, okay, that first code word, I want you to tell me the value at index 14 and index 28. And also in the next code word, tell me the value at index 14 or maybe 17. So those 3 values, they're supposed to be connected based on some formula. So when you give me those 3 values, I will now use the formula to check whether code word 1 is correctly related to code word 2. But then you cannot lie about what those values are at index 14 and index 28 because we have already done a Merkle commitment. So when I ask you to give me index 14 and index 28, I'm expecting the values, then also a Merkle proof for each of those. Yes. So I'll verify the Merkle proof first. Once it is valid, I'll now take those 2 values or the 3 values that you have given me. Then I'll plug it into the formula to check whether these 2 are related. Now the fact that you don't know where I'm going to ask you to open means that you have to be honest. Because of if you knew exactly where I was going to ask you to open it at, then you can just make the values correct at that point for the formula. So that's why the commitment has to happen before the query phase, to make sure that the guy is like bounded. You can't change it again. And if you know you cannot change something, it's like you know that you are going to be queried or there's going to be an exam, but you don't know the question that is going to come out. then you are forced to study everything. But if you knew the exact question that is going to come out, you just study that question and then just go there. It's even worse than AOC. This one is like you know the exact. Exactly. So that's the power of that's the power of like ambiguity. That's where randomness comes in ZK. It's like it makes sure that the prover cannot know where it will be tested at. And so the only way to cheat, or the easiest way to cheat, is to be honest, which is like not cheating. Because you just don't know. Make sense?
So I'm looking at every folding here.
You mean the Merkle proof?
Yeah, I don't understand now.
Yeah, you're going to. So out. Yes, you're going to open every. Yeah, so you make a query at the top. And that query at the top will basically say, give me one value. And then give me A, the value at A, but also give me the value at minus A. Then those two will be linked to a new value in the next one. So we use the formulas to check that it's linked correctly. Then now you have a new value in the next layer already. So you give the minus, so like A square, then maybe minus A square. Then you link it downwards. So you just continue linking it downwards until you get to the constant, which you can then verify yourself. Cool. Let's do for one more folding so that we can get a constant. Okay.
So, are we not following this?
I want to fold it now. Yeah.
So I thought you said when we get to this point, sufficient enough.
It depends on the. You can stop here and send the code word. It depends on the block factor, right? You know, like this is a degree
This is a good one, though.
1, which means like it can be represented with 2 values, right?
Yeah.
But let's say your block factor is 16. Then that means you need to send 2 times 16, right? Which is 32. So it's not every time that degree 1 is like small enough.
Well,
You-
after the next reduction now will give us a
Constant. So there's no degree again. So it's just like
So it's just constant or every point, no matter the number of
you get. So most times like better to just go to the constant, depending on your block factor.
Well,
But it's for X. I mean like the reduction. And when we'll get there. Yeah?
you know, say you mentioned something that really where this stop is kind of like an argument.
Yeah.
So you can decide to stop at a degree higher than one.
Yeah. Depends on the computing resource of the verifier. So the verifier feels like, oh yeah, like with 0 now, I think they stop really high. Like because their program trace is so large relative to they stop at a pretty high degree. But they know that the verifier can handle that. Make sense? Because you could literally like not even do anything and then just send the full poly itself, right? And then the verifier will just so all of this is just to make the work easier. So now let's fold this. We need our new G3 of X, right? That's all the even powers. That's just 155. Then we need our H3 of X. You need just 84.
Yes.
Yeah, it's 4 because we factor out the X, right? So we now get our R. Let's say our R is 2 now. This is our R3. So that's just going to be 155 plus 3. Sorry, 2. Right?
Okay.
What's this? 155 plus 168. Then 168 plus this is what?
2.
Yeah. So this is the last poly slash code word. So like blowing up this is not really blowing up in read Solomon, right? Read Solomon is like you interpolate it and you evaluate it at all the roots of unity. What's the interpolation of this? 323, a constant poly. There's no x. So if you evaluate it, it's just 323, 323. So it's like this is enough to send over. Does it make sense? Let's now do a. It's not a lot because of it's repeated. Like it's just going to like a for loop.
Yeah.
It's just going to be a for loop log n log the degree, right? And it's in evaluation form. So you're not doing all this. You're not seeing all these symbols. You're just seeing a vector of numbers that you just interleave and fold. Then you have the new one. Then you come back again, interleave, on and on like that. It's not a lot. It's not a lot actually.
So you said this is the evaluation form.
Yeah, when you're actually implementing, it's going to be in evaluation form. I'm just explaining in
Yes, but
creation form.
okay, so okay, give me evaluation form. We're talking about what?
Rest of it. So it depends. At the beginning, maybe just your polynomial in evaluation form or something, or creation form. But then when you get the code word, it's going to be evaluation form over the roots of unity.
Okay, so that means I get your polynomial when you convert it to the
You get your polynomial,
evaluation form, then what's the equation?
or you start with creation form, then you evaluate that polynomial
Over what?
over the roots of unity.
Okay.
So you now get like a vector of field elements. Do you get? Then that was now going to serve as your
So
code word.
what is the unity when you go log into you get something like this.
You will get no, you will get something like this. Where each of this is a field element. So you evaluated this polynomial at w0 raised to the power 0, w raised to the power of 1, w raised to the power of 2, up to w raised to the power of n minus 1. So this is now your first code word for the polynomial you're trying to commit to, right? This would be enough if the prover could trust you on the degree. This commitment is enough. But the prover cannot trust you on the degree, so you guys need to do the with Solomon interactive oracle proof of proximity, which now means that you now take these two, right? Commit to it, send the root hash, verify will give you randomness. Use the randomness to fold this f into a new polynomial. That new polynomial is going to be
Maybe I'll ask you this question. How do you like identify the or I mean we are going to like question for you.
yes.
We're not asking about the forms again about example because of how do you identify the or
Based on the arrangements in the array.
and that's what because they
To be 0, 1, 2, 3, like the power of the array is already 0, 1, 2, 3. So the evens are
Yeah, I get your point. That's true. I think I'll get back on that. I have to go and look at the detail. Cause my initial idea was like, okay, you just do this, and then you just take this here, right? Then you do this, and then you take that one there.
yeah.
But then you're not going to necessarily have like 5, 30, 9, and 15 anymore, right? But there might be some relationship between the evaluations and there will be some relationship between the evaluation and this interleaving also. But I have to like run the math just to verify that.
Is this like doing
So are you saying like sometimes the numbers might like the powers might not be in order?
No, it won't even be in this form. It will be in evaluation form. You know, the code word is the evaluation form of this polynomial.
yeah.
So like the current way that I'm saying that you can do this, like, oh, you still use like your regular FFT, the same way you did for the first one.
Yes.
But I feel like there's definitely a better way. But I need to run the maths. I'll just say that, oh, the evaluation form still holds that structure, that when you split it like that, but I need to verify that. Did you get?
Sorry,
I'll do that.
question.
Yeah?
So when we get the evaluation, the first code word basically, right? And
Yeah.
we are interleaving to find this different given terms and odd terms, right?
Yeah.
and you know like the formula is basically like g of x plus r h of x.
Mm-hmm.
Where does the r come in? Like if you just multiply r with
Yeah, I think you just scale out more
just
R
scale
with,
out more.
I think. But now that the coefficient is not the same, I need to verify that. But I think you just multiply R with the. There's a. There's a relationship. We might do it here actually. I'm coming. I'm trying to draw out the. Does it make sense? Cool. So the proof is basically the macro root of the commitment, sorry. Macro root of this, macro root of this, macro root of this, and then this one is like the actual constant. So the commitment is equal to does it make sense? Hmm?
Comments like this, all the root hashes essentially.
Yes. Combine all the root hashes of all the folded, all the polynomials, including the top one, except for this one.
So you're Meku committing each of them.
Yes, I'm not commenting each of them. Does it make sense?
Yeah.
Sorry,
That's
what?
that Meku commitments that you did at first.
Mm.
Like when you use each of the array elements
As a leaf.
like mapping to like this tree to get the final root. That's the same thing you're doing for all of them.
Yes. So like if you're implementing, you have like a Merkle struct that has a commit function that takes a slice of field elements of a power of 2, and then it just like generates the root hash for you. That's the output.
So that means that Meku whatever now is also going to have the authentication.
A prove and a verify. So for proving, you specify the index, right? The index you want to prove. Then you now give the sibling, then give that one sibling, then give that one sibling, then give that one sibling.
Then
Then
for the verify.
for verify, you pass in the proof, and then it's just like hashing, it's hashing each of them.
Check the final output
Is equal to the root hash.
So it's
Which one?
what is the national like for the commitment?
It's for, so, you remember the macro, yeah, this one. So the proof is this, remember? And this is what you're trying to prove. So to check if it's correct, you merge this with this by hashing.
How does that relate to the commitment and the N1 and
No, well, I was talking about Merkle tree verification. So like the Merkle authentication part, when you prove membership in the Merkle tree, how do you verify that? That's this.
So in the case of those, like that final, that one, how do you, what's
In FRI,
Yeah, the FRI.
the last thing we did, right?
Yeah. What are you verifying?
So next thing we're going to do now is we're going to do something called consistency checks. So what we're trying to do here is we're trying to verify that this M2 was gotten correctly from this M. So like this code word was gotten correctly from the code word above using the R that I gave.
Who is doing the draft?
is both of them. So it's like they're going to a new phase of interaction. This is the first phase. This is the commitment phase. All that happens is prover, polynomial he wants to commit to, right? Turn into a code word. Meko, root hash, randomness, fold, Meko, root hash, randomness, fold, Meko, root hash, randomness, fold, on and on like that until you now have the constant. So that's just, you can see how quickly I was able to describe the commitment. So that's how quickly the code too.
So what's the point of that? What are we going to do?
The point of FRI is to ensure that the polynomial you're committing to is bounded by a certain degree.
It's bounded by a certain degree.
Yes.
That is all.
Yeah, and it's a polynomial commitment scheme now. Like it still has the polynomial commitment scheme characteristics. Like it's like an interactive oracle proof of proximity. Like the real purpose of FRI is to. So FRI, the full meaning of FRI is called Fast Reed Solomon Interactive Oracle Proof of Proximity. The full meaning of FRI is like fast. So I think they call it like FRI IO.
Oh, Solomon is oh.
It's not a PCS. It's an IOPP.
Oh, FRI is an IOP.
It's an IOPP. Yes.
IOPP.
Yeah. IOP is interactive oracle proof. But now it's a special type of proof that it is proving, which is like proving proximity of this guy to a degree, let's say degree 8 code word.
Wait, so FRI is an IOP.
IOP, yes.
Extra P.
Yes.
So you're saying that I thought FRI is like a PCS, like
It can be used as a PCS. So once you have any interactive oracle proof of proximity, there's a way to convert that to a PCS. So what you need to solve, or what researchers need to solve, is creating better IOPPs. So once any new IOPP comes, that is instantly also a PCS, because we have a compiler that can compile an IOPP to a PCS using that quotient thing that you guys did in KCG, where you want to verify that f of r is equal to v, right? So that's going to be like f of x minus v should be divisible by x minus r to give you a quotient. This is how you also do it in FRI. But just that now you prove this relation differently using an IOPP. Wait.
What was the advantage since this could that as a PCS? What was the advantage over PCS?
Firstly, it doesn't use elliptic curves. It uses just hashes, which is like Meko root hashes, right? That's like post-quantum, possibly. Then I think they call it, they say possibly post-quantum. I don't know why, but I think it's post-quantum. I don't think it's even possibly. I'm coming. I don't think Google knows what stacks are. I have to put ZK in front. Nothing about quantum. You see, I don't. This thing now is like wordings, right? What do you mean by widely believed? This is not be a belief thing. So that's why I'm like plausibly post quantum. Because if it's definitely post quantum, then they won't say believed, right? And this from stackware.co. So that's like it's them that actually wrote it.
But everything is still based on assumptions and belief. It is believed that quantum computers are going to. It's still believed.
Yeah,
I'm not saying it.
yeah.
It's still believed.
And but this statement now is based on like the assumption that okay, quantum computers are here, you know. So will it be? I guess they are not sure maybe what the powers of this thing will be, or I don't know. But yeah. So which one? Okay. Yes.
So,
So the only cryptographic primitive is a cryptographically secure hash function, which we denote as H. Non-quantum vulnerable forms of cryptography all depend on some other cryptographic primitives. I think you gave a clue.
quantum secure attraction.
It's not parallelizable.
Those GK stacks are using FRI.
Yes. Stacks
Just
are
like
using
snacks
FRI.
are using GKR.
No, that's so Fry
Yes.
is the PCS. It's
For
used as the
stack.
PCS
For stack.
for the stack IOP
Okay.
or PIOP. PIOP actually. I need to teach you guys this. I think we might even just do that today. So that you can see the full, because the picture is so simple, and then you'll be able to see where all the researchers are like. You can see like, oh, this is the tree. The researchers are just like changing this branch. Like, oh, this branch, I don't want this one here. I want this other one here, and that's just what they're doing. But I'm coming. I want to finish this thing. So this thing, they're just not sure. Like, there's no proof that anything.
It's not parallelizable. So, from what you said yesterday, that's where competent has shine. So, since
But this
it can't be
Grover's.
parallelized,
This is Grover. So I think they're not trying to relate hash functions with.
okay, the global is supposed to be a solution.
Yes. Wait, no, that's not that. So it said no one has been able to generate any structure, demonstrate any structure within SHA-256 that will lead to an approach superior to Grover.
So, it's still going to take, it's going to take 100 quantum computers to solve it. It's not practical yet.
I guess.
Yet.
Maybe that yet is the
Next 3
possibly post quantum. But we know that KZG is not. Right? Once quantum computers are here, if they are here, who knows? Then it's that one is gone. Right? This other one is still under maybe. So what did we want to talk about? Was there any question?
Yeah.
Yeah.
So I wanted to ask, you say that GKR is like
The
basics,
IOP.
the
Yes.
IOP for snacks. Like
Yes.
when you
For
now-
some snacks.
For some.
So it's like they'll crucify me if they hear this outside, but snacks it's like the body and then stacks inside there somewhere. Do you
Inside.
guys? So like all the proof systems
Yeah.
is just some information theoretic protocol plus a polynomial commitment scheme. GKR is an example of an information theoretic protocol. Sum check is an example of an information theoretic protocol for a very, very specific problem. It's not like a general, it's just like summing all elements in a vector. That's what sum check is good at. GKR is more like general. Then stacks too, they have their own. Then Plonk has its own. Gross16 has its own. All of them have like their information theoretic protocol. But to now make it succinct, you need a PCS. So all the messages that you're sending over Rather than sending a message in full, you will now send a commitment. That's what's going to make things succinct.
Yeah. So I remember that in one of the class, we were like, we are going to implement GKR, and that's like snack. Now once you implement GKR, that is like you implementing snack. Then
And it's a
although
snack.
it's like the
It's a
basics. When you now add PCS to it, you now actually make it a snack.
it's a knack
It's a snack.
without the PCS.
Okay, it's a snack without the PCS. Okay, so once you add PCS to the NAC, it now becomes a snack. Now, my
So
question,
if you don't add Fiat Shime,
yeah,
if you don't add Fiat Shime,
yeah,
it's an act.
it's an app.
Uh,
Okay, so now, now my question is, right?
I'm coming.
Nah.
So that's what I use like GKR,
Ah, right.
interactive.
Good.
And this one is plus Fiat Shame. And this one is plus.
Don't let me get.
Alright. So now, what is, since GKR is the basis of,
It's-
is the basis, now is the arc,
It's one of the acts.
is one of the arcs.
Yes.
One of the arcs of snacks.
For
I
example,
use GKR for stack.
it depends on what you define as stack. Stack is scalable, transparent, argument. Is it argument of knowledge? Is that it?
Yeah.
Okay. So now the T means that it has a transparent, trusted setup. The time that this terminology came out, all snacks were based on trusted setups, like we did in KCG, right? Because of the PCS. But now, with GKR, and if you use something like base fold, like right now, you guys will still be using like a trusted setup because we are using multilinear KCG. But we are using base fold, or FRI Continued, or Ligero, or breakdown. You are not using a trusted setup anymore. And because of that, it's technically transparent, right? So that transparency is just, they were just trying to distinguish because at that time, everybody was using trusted setups. Gross 16, Plonk, everybody was using trusted setups. So they were trying to like distinguish themselves that, bruh, we don't use trusted setups here. So that's why they put that T, transparent.
So that what I want.
So what I'm trying to say now is that snack is a more general, because it doesn't put any restriction to whether like, oh, it is transparent or it is non-transparent.
It's not transparent now.
No, snack can be transparent. No, non-interactive.
Non-interactive. Okay.
It doesn't put any restrictions whether it's transparent or not transparent. So that means it is like the
General.
exactly. So stacks now, you are a snack that is transparent. Go there. Then the other ones go there. So that's why I'm saying that snack is
Okay, so that means GKR can also be used as
technical.
snack.
But they will crucify you outside. You said.
But if GKR is the arc,
Yes.
and there's arc in stack, there's arc in snack.
Yeah.
GKR should be used in both.
You could. It's just
So
terminology.
So, okay, this is my question. Is there an IOP
Yeah.
that is particular to stacks?
So based on like the stack, let's say like Stackware,
Yeah.
they have their own. The IOP is just Swaziku lemma, to be honest.
Say?
The IOP is just Swaziku lemma.
Swaziku did my IOP.
It's not really an IOP. It's just like an IOP is a protocol, okay, between a prover and a verifier, where they exchange oracles. I need to explain everything. Let me just explain everything now. Just start from scratch. So you have what? An information theoretic protocol, right? Plus a PCS. Okay? An information theoretic protocol is sufficient for the prover to be able to convince the verifier of a statement. Like it's already sufficient on its own. I'm describing it now. Okay? Then they're not like three different types that are currently being used right now, but it could be anything. So at the okay, let's start from the beginning. You have NP. Okay, this complexity theory. NP is the set of problems that you can easily verify. So it's always like a problem solution statement, right? So you have a problem and you have a solution. This is not the way, like if you go to like computer science, they're talking about language, and then they're talking about like membership in a language set. But it's still the same thing, okay? So problem, solution. So you have a problem and you have a solution to that problem, like Sudoku problem, and you have a solved Sudoku. Now, MP is the class of problem solutions such that you can easily know. Okay, let's talk about P first. So P is like once you have the problem, if you see the problem, you can easily get the solution. And when I say easily,
when you say easily,
yeah,
that
let
is
me-
grammatically or computationally.
in polynomial time.
Like we are dealing with computationally now, not just like human we solving it.
When I say polynomial time, I don't mean math polynomials. I mean like you can express the time it will take to solve this problem as a polynomial.
Polynomial.
Yes. Do you get?
That's still polynomial time.
That is polynomial time. So it's just telling you.
It's not referring to computer polynomial.
It's just telling you how long. Just know that okay, polynomial time is something that you should be able to wait. You should be able to wait and see. Yes, O of n squared, O of n cubed. Then when you now leave that n squared, n cubed, then you're not talking about also like exponential time. But if you see the problem, you can solve it in polynomial time. So that means like there's an algorithm that can solve this problem in
Like a finite amount of time.
it's always finite. Like if you have all the resources in the world,
Yeah.
something that is running in exponential time, if you give it enough time, it will end, right? But it's just that like you can search all possible Sudoku solutions. At some point, it will end. You are probably just dead, and all your family members are dead, and Earth is gone, and the sun. That's just the difference, right? But polynomial time is like, I think there's still some polynomial times there, but let's just forget about that. So the main point is that if you see the problem, you can get the solution in polynomial time. And if you see a problem solution pair, you can check whether the solution is the solution for this problem also in polynomial time. So you can solve and you can verify in P time, right? That's P. Now there's NP. So NP is like you are given a problem. If you just see the problem, finding the answer is hard. It's possible, but it's hard. It's going to take you some time to find it. Non-polynomial time. Yes. So it's going to take you a while to solve that problem, and so, but then once someone else gives you like, oh, this problem, this is what the solution is. So this solution, there's another name for it. It's called the witness. Should have heard something like that in ZK. So once you are given the witness or the solution, you can easily check whether this solution matches this problem. Like quickly in polynomial time, it's still the same time as this. The only difference is that you cannot solve it in. So that's P versus NP. So usually it's like the statements that people are trying to prove are usually NP statements. So you're trying to say that okay, I have this problem. I need a solution to this problem. Usually the proof is the witness. So the proof is the solution. So Sudoku, there's a statement that you know the answer to this Sudoku problem. That's it, right? You have a Sudoku problem and then someone says that I know the solution to this Sudoku. Now that person, to prove it to you that they know the solution to the Sudoku, they are going to present to you the solved Sudoku, which is the witness. And you can easily verify that that witness is correct for the Sudoku by checking that all the rows are 9, columns 9, and then the boxes are 9, and all the things that were already in the original solution is also in the solution. In the original problem is also in the solution. Make sense?
Yeah.
Now, the ZK people were now like, is there another way for me to convince someone that I have the solution to an MP problem without giving the person the witness? That's where that zero knowledge comes in. Because the naive way is just to give the person the witness. They were not like, can we do it without giving the person the witness? So some people just started thinking about that problem as a puzzle, alright? And then the person that wrote GKR, one of the persons that wrote GKR, the G there, with somebody else, were the people that invented the field. Imagine like just following curiosity. They figured out one thing, just one paper, and you guys are here now. Do you know how crazy that is? Like the effect of just figuring out that one paper made this possible. That's crazy.
Always
Yeah.
this sorry, this MP, I think the problem that tries to is not really MP, it's MP complete problem.
Not necessarily.
Like I think there's an article I was reading that maybe there are classes of MP problems
Called MP complete.
that are called MP complete. So there are some MP problems that are solvable. But the class of problems that is to recognize an MP complete problem.
There's MP complete, there's MP hard.
See, MP complete is like a class of problems that once you solve one, you have solved all the other MP complete. Because of you can translate one MP complete problem into any other MP complete problem, right? But then they're all still MP. It's just that it's a subset of NP that they are now grouped together. It's like you have NP, then maybe we now have NP com. I don't know if it's like this. It might be.
Yeah, MP complete.
Then now, all the problems here can be written as one another. So if you have a solution, a program that can solve, let's say, protein folding, like real quickly, then you instantly have a program that can solve maybe Sudoku really quickly. So people have chosen this thing called SAT. SAT is called circuit satisfiability. It is MP complete. Now they have like put so much effort into finding great algorithms for SAT, which now means that they can convert most problems. So everybody just focused on finding good algorithms for SAT.
But according to
Nah.
pop culture,
Wait. Then they can now convert any MP complete problem into a SAT problem instance and then use the SAT algorithms that they have discovered to solve that. Then once they solve that, they will now convert the answer back into wherever they came from and then send that. You want to say something? Do you have a charger?
no,
Do you have a charger? Your charger.
But like according to pop culture, like the
No, this one. Can you
Yeah, I'm listening.
yeah, but according to pop culture, like you normally use like Sudoku, this and that.
To what? To solve?
Yeah, like that's why there's this thing that you can solve you can find a way to easily solve Sudoku. You have indirectly found the cure to cancer.
And that
Based on both of them
is
are
MP complete. Yeah. So if you can find a way to solve any one of them, then you can find a way to solve all the other ones. Alright. Because of you can translate every problem in that to any other problem in that space. So if you have a problem like protein folding and you have Sudoku, there should be a way to find a Sudoku problem that is equivalent to that protein folding problem. So if you solve that Sudoku puzzle, then you have instantly solved the other one. You just convert the answer back into protein folding. So let's continue. So now that we have, so they now came up with, these guys, the first guys, they came up with something called IP. IP. So IP is called interactive proofs. That's IP. So that's like you have a prover, you have a verifier, and they're talking to themselves. Okay, that's the interactive. So the prover will tell the verifier something, the verifier will ask further questions, then the prover will tell the verifier something else, the verifier will ask further questions. So the way they did this is you said? For example, like where is Waldo and all those things. The way they did this is it's going to ask you questions that only if you have the witness will you be able to answer it. Okay? So if you have the witness and it asks you the question, you'll be able to answer that question. Now, if you don't have the witness, there's a chance that you might be able to guess the answer to that question. So there's a very good example, like colorblind. Okay? I am colorblind. You are not. Yeah, I'm colorblind and you are not. Then you have the statement that I am holding 2 sheets of papers that are of different colors. Now, me looking at those 2 sheets of paper, there's no way I can know whether they're actually of different colors or not. So I need a way to still convince myself without, even though I'm colorblind. So what I will do is that I'll take the 2, right? Let's say this is red and this is blue. If they were not of different colors, it would be red and red, for example, right? So now, that's already created a distinction. So what I'll do is I'll put it behind my back, and then I'll decide to either swap it or not swap it. So if I swap it and I bring it out, if they are indeed different colors, you will know that I swapped it, right? So I'll ask you, what did I do? Did I swap it or not? Then you will tell me, yes, you swapped it. Now, if they are the same color, you are not supposed to know whether I swapped it or not. So you should not be able to answer that question correctly, only by luck, right? So you just say you just guess. Then there's a 50% chance that you guessed right? So that's why I'll repeat the process again. I'll do it multiple times. There's no way that at some point you are not going to make a mistake. But someone that is actually saying the truth will get it correctly every single time. That's an interactive proof. Like me, the prover, and the verifier, we're interacting to answer or determine the statement. But then I never get the witness, right? I never see the color of the, because of I'm blind, right? Yeah, the verifier is blind, and then the prover is. So that's an interactive proof. You have a prover and you have a verifier, and then they just do back and forth interaction. This is where some check falls under. This is where GKR falls under. Okay? Then after interactive proofs, they created something called PCP. PCP is called probabilistically checkable proofs. Okay? PCP, probabilistically checkable proofs. The idea is this. Let's say you are a math student, right? And then you generate you have a statement, right? And you write a proof for that statement. Then you give that statement to a reviewer, right? The reviewer is supposed to read every single line of that proof to be convinced that the proof is actually correct, right? Probabilistic checkable proofs are basically like you create a proof that the reviewer only has to look at 1 or 2 spots, or maybe just 1 spot, maybe like 1 letter in your proof. In your entire mathematical proof, you just look at 1 symbol, maybe sigma somewhere. And just by looking at that sigma, the person is convinced that the proof is valid. That's what PCPs are. It should start reminding you of like Schwarzenegger lemma.
Yeah, I want to check.
Like I try and check if 2 polymers are the same, but you only check it at 1 point, rather than checking at all the points. That's PCPs. Huh? Yes, exactly. So the way you do that is that you take the original proof and then you just blow it up. So let's say the original math proof was like 2 A4 papers. When you now blow it up, you're going to have like 500 or 5 million A4 papers. But now that you have this, you can just take one of them and just look at one character, and then you're sure that every other thing is correct. But then the prover had to do a lot more work to build that's PCPs. So what happens with PCPs is that you send what they call an oracle. This is where the oracle comes in. No, not an oracle. You send a proof. You send just a string. Yeah, you send a string. The prover sends the string to the verifier, and then the verifier will just check maybe one entry in this string. Okay? And then once it checks that, it's sure that every other thing is correct. Now, they now merged IOP and PCPs together. This was recent. IP, sorry, and PCPs. So they got IOP. And IOP now is an interactive okay. So now it's interactive again. PCP was not interactive. PCP is like, I have my proof, I blow it up into 5 million A4 papers, and then I send every single thing to you. Then you just check one. Not interactive, one time. Now IOP is like, you do IPs and you still do IOPs. Okay? So now you have the prover, you have the verifier. Then the message is now an oracle. So an oracle is basically a string, but you don't send everything to the verifier. You send like a promise that if you ask me to open anywhere, I'm not going to lie to you. You get? So you're sending the oracle, but then the verifier can query any part in the oracle and be sure that the answer is going to be what it truly is. Okay? So every message is basically an oracle. That's what interactive oracle proofs mean. The messages are oracles. Make sense? So you now use commitments to instantiate oracles in the real world. You know, like the promise is that I won't lie to you if you open. So PCS are kind of like allowing you to simulate that situation.
Like it doesn't lie, I would like to read it.
No, it won't lie to you. Yeah. So, but then you now use cryptography to ensure that it really doesn't lie to you in the real world. So that is like a model where everybody is assumed innocent, kind of honest. So those ones now are, we are now using them to make these ones succinct. This is what I'm describing here is like the information theoretic. KCG and FRI are here. Okay? PCS. So this is what they call an IOP. Then there's now a version of an IOP called a PIOP. So the oracle is just think of it as like, instead of sending you the string like I do in PCP, right? Like I do in PCP. You know, you're sending all these PCP strings. Instead of sending you the string, what I'm going to send to you maybe is like a trusted third party or something. Like a guy that won't lie. Okay? Not like a transcript. That's like fair sharing. Just like a guy that would not lie to you. But he has this PCP, this string in his head. You know, in PCP, you don't need everything there. You only need a part of it. So it somehow doesn't make sense to be reading everything from the prover, then just checking just like one part. So this is not like helping you not have to read everything. But then in that case, I'm now sending you somebody that knows everything. So then you will now ask that person that, okay, I want to read page 542, character 13. Then the person will now tell you what. But this person is trusted not to lie to you. about. That's what the oracle is like standing in for. Does that make sense? So then now come PIOP. PIOP is exactly the same thing as an IOP, but instead of sending oracles, instead of sending like strings, you are sending polynomial oracles. Okay? So rather than sending like a string, you are sending P1 of X, P2 of X, P3 of X.
Subject.
Somehow, exactly. These are like the round polys, for example, or Plonk, or so almost everybody now uses PIOPs for their information theoretic
What's the
part.
meaning of
Oh, polynomial. So now this is saying that I'm going to send you polynomials, but I won't give you like the full polynomial. I'll give you someone that knows the polynomial. That's the oracle part. Then you cannot ask this person to open that polynomial at any point, and the person will not lie to you. So you ask the person, okay, what is P1 of X evaluated at 5? And the person will give you what the answer is. That's the oracle. You can see that all these things are kind of like very trusting, right? That's where cryptography now comes in. Cryptography is not like, I know this thing will not work in the real world. They are adversaries. So now, how do I ensure that someone that is trying to cheat me cannot cheat me, even if they wanted to cheat me? That's where cryptography now comes in. So like, someone is supposed to stand in place of this oracle in the real world. That person could lie. How do I ensure that person cannot lie? So these are all the information theoretic protocols that are being used now. Everybody has kind of like gone towards, yes. That's why you're always hearing polynomial commitment schemes and everything. So now if it's IOP, so the commitment schemes are now what you use to make everything succinct and like trustless kind of, right? So the IOP case now, this is a string. How can you get somebody to not lie to you when you ask the person to open one element in that string?
This thing can be applied to real world situation for nice.
It is now. So
Everyday conversation with people.
oh, okay. So how you guys should know this now. How do I ensure that? How can I force someone? If I say open this string at index 1, no. How can I make sure you're not lying to me?
So
How
ask
do you make sure
You
that?
commit it with what? With what?
Come again, please.
Come again, please.
I have a string of values, right?
Okay.
I want to ensure that when I ask somebody in the future, what is the third character in this string, that the person will tell me the correct thing.
Is it not the same thing as that
Okay,
Meko?
you can create a commitment.
A Meko commitment.
That,
So you
when
get,
the
is it
person tells you,
Meko commitment?
yeah, when the person tells you that it provides proof.
Exactly. So that is how you can create an oracle for a string in the real world. This string is serving as the vector. And you know Meko trees are good for vector commitments. So that's how you can convert an IOP to a snap. So you want to go from an IOP to a snap, you just, instead of sending oracles, you send Meko root hashes. And anytime the verifier wants to query that oracle, it's going to ask the prover to generate a Meko authentication path. That way it's sure that it's like serving as the oracle. You cannot lie anymore, but we're instantiating it with cryptography. Does that make sense? But now for PIOP, you cannot just use the Meko commitment, right? Because now this is a polynomial IOP. This is no longer a vector. So there's a degree component that exists here. Does that make sense? So that's why you have to use a PCS instead of just a vector commitment. You need to use a polynomial commitment scheme. So if you want to go from PIOP to a snag, what you do is that you use PIOP, then you now use the Reed-Solomon interactive oracle proof of proximity to convert it into an IOP. Then you now use a Meko commitment to convert it into or a
Why do you convert it back to an IOP?
why convert what to an IOP?
PIOP.
So to convert PIOP to an IOP is like use the RS IOP, the Resolomon Interactive Oracle of Proximity, to prove the degree. You know, it's two parts now. Polynomial has degree and values. You need to prove both of them. So you use the RS IOPP to prove the degree. Now that the degree has been proven, you now have just those code words at the top that you trust now that it's of the right degree. Then those code words, you're using the MECO root in order to prove the values.
So in essence, we are using the whole Solomon interactive.
Yes. So like FRI is like doing both the RSIOPP and the.
So talking about commitments, you know, to push a prime feed element into transcript, for instance, you have to do all those convert to byte and to big byte and stuff like that. Now, if you want to push something like a commitment which has a generator field and stuff like that, how, like, what's the logic
You want to
push that commitment to transcript?
What is it? Is it a field element? Is it a group element?
No,
Is it a router?
generator.
Which generator?
It has a generator in it, like.
Are you talking about multilinear KZG?
Like yes, like KZG with multilinear.
Like
KZG.
groups,
Yes,
electrical
like,
groups.
Yes, like that commitment form. That is.
So I don't know specifically, but the idea is that all the information contained in that object, you need to somehow put that into the transcript, which means that you might need a way to convert it into everything. At the end of the day, is all ones and zeros. So there should be a method somehow. I don't know what the method is.
On the generator.
Yes, on a group to convert it to bytes. On a group element, convert it to bytes. And then once you have that, just put that in. All you need is all the information there. You should be able to like get it. Just don't leak information. Like everything that's supposed to be put must be put. So I think like indirect. Indirect. Okay. But I don't know the exact method. You just have to check like the.
No, you just don't want to.
No, I don't know it. I do not know it. But are we good? Does it make sense?
Yeah.
So that's basically. So research now. People are finding better ways to do.
Better ways than FRI.
Yes, better ways than FRI to do the RS IOPP. So there's already FRI. There's where. There's stir. There's there's Blaze. So some of them don't even use like Reed Solomon anymore. So sorry, this space is not RS IOPP. This space is like IOPP. RS IOPP is just for Reed Solomon. But you could have used another code scheme that is not Reed Solomon. Then PIOPs, people are finding better other protocols for PIOPs. So like GKR, SumCheck, other protocols, right? For the PIOP side. So it's basically just like information theoretic protocol plus a PCS. People are innovating on this side. People are also innovating on this side. Most of the innovation right now is coming on the PCS side. Like they're just releasing different polynomial commitment scheme papers.
So, maybe like the KZG that we did.
That was the oldest. Yeah. But that's just one PCS. So there's like multilinear PCS, and then there's univariate PCS. And then there's now binary field PCS, which is like FRI, Binius. And there'll be more.
FRI is a PCS.
FRI is a PCS for univariate polynomials. Then basefold is an adaptation.